untuk mendapatkan informasi terkait dengan pertanian. Materi ini akan disampaikan oleh para pengajar dari Planetek Italia. Sudah bergabung bersama kita Dr. Antonio Novelli, seorang pakar remote sensing dari Planetek Italia, sebuah institusi remote sensing yang berkecimpung dalam pemanfaatan data-data geospasial dengan lingkup kegiatan mencakup akuisisi, penyimpanan dan pengelolaan data, hingga analisa dan pemanfaatannya. Setelah sesi pembelajaran nanti, kita akan sama-sama bertukar ilmu dan berbagi pengalaman tentunya dengan narasumber dan para pakar yang sangat menarik untuk diikuti. Hari ini akan bergabung dengan kita Dr. Insinyur Dede Dirgahayu Domiri, peneliti Pusat Riset Pemanfaatan Pendidikan Jauh, Organisasi Riset Penerbangan dan Antariksa Lapan, Badan Riset dan Inovasi BRAIN. Kemudian juga akan bergabung Ibu Dr. Rizatus Sofiati, peneliti dari Balai Besar Litbang Sumber Daya Lahan Pertanian Kementerian Pertanian. Sesi knowledge sharing ini akan dipandu oleh moderator Dr. Firman Hadi. Baiklah Bapak, Ibu, dan hadirin sekalian, untuk mempersingkat waktu, kita akan mulai sesi pertama pembelajaran yang hari keempat ini dengan memanggil Dr. Antonio Novelli. To Dr. Antonio Novelli, I offer this time and screen to you. We would also remind you to have a first break for 10 minutes at 2:30, and now the time is yours. Thank you.
Okay, thank you, Nancy, and good morning to everyone. First of all, first check, can you hear me?
Yes.
Yes, okay, perfect. Now I'm going to share my screen in order to start the training session. Can you see my screen?
Yes.
Okay, perfect. So again, good morning to everyone. I'm Antonio Novelli, Senior Technical Specialist from Planetek Italia, and today this is day 4 for this training, and I'm going to talk about the activity carried out in this project, and also some, let's say, basic definition before to start to show the results of this project. So first of all, I'm going to talk about the definition and basic principle of passive remote sensing, considering electromagnetic radiation, some info of so the energy that is detected by remote sensing sensors, some radiometric quantities, because before, talking about vegetation indexes, classifications, and portals to, let's say, get geoanalytics, we should first of all understand where the information comes and how it is recorded. Then we are also going to I'm also going to talk about the interaction of electromagnetic radiation, just to give some insights on, let's say, why it is needed to perform an atmospheric correction on digital satellite images. And then also spectral signature, it's something that we should introduce in order to understand why vegetation indexes might be useful and why we can use them. Then I'm going to talk very briefly about the Copernicus program and Sentinel constellations, because I might imagine that during this training, the Copernicus programs has been already mentioned several times, so I'm not going to spend a lot of words on the Copernicus program, but of course I am available to clarifications if asked. And then vegetation indexes, so something related to the project. Vegetation indexes are result-focused analysis and land session, and an introduction to land use semi-automatic classification. Especially, I'm going to talk about the algorithm that Planetek Italia implemented to restitute the land cover products for this project. So, regarding the please feel free to interrupt me for asking questions, and of course I'm available to answer to your questions. So first of all, when talking about passive remote sensing data, we should mention the electromagnetic spectrum. We should mention, as said before, radiometric quantities. So let's say what is measured by the sensor, and thus what is the information that we exploit for our analysis. Another important topic to mention here is, let's say, the interaction of the electromagnetic radiation, so the light, the information. When I mention the electromagnetic radiation in passive remote sensing, it means I'm talking about the information that we process. So the interaction of this information with the atmosphere. And then, as said before, we are going also to show some info on the spectral signature, and I'm also going to, let's say, to talk about some practical tips for the definition of vegetation indexes, starting, for example, from a spectral signature. So let's start with some few words on the electromagnetic radiation. So the electromagnetic radiation, as I told before, is, let's see, the energy, is the information that a satellite, a passive satellite, so a satellite that is only able to detect the information that is reflected or emitted by the Earth's surface, and not has, let's say, active sensors. It's able to detect the information that, let's say, is emitted by the satellite itself. The electromagnetic radiation is very important to know, because it is the information that we process, that we detect. When we talk about electromagnetic radiation, so information that we detect and process, it is very important to know that this information is can be represented and classified in the so-called electromagnetic spectrum. Normally, the electromagnetic spectrum is, let's say, a representations of the different ranges of electromagnetic radiation that we use to represent the different range of wavelength and frequency and energy, so of the information that we detect. We have here the radio waves. The microwaves are, let's say, the ones that are used in active remote sensing data. So, for example, in Sentinel-1. Then we have the near-infrared sphere, and that is also detected by passive satellites such as Sentinel-2 or Landsat 8. We have the visible portion of the spectrum, that is that portion of the spectrum detected by our eyes, and then we have the ultraviolet, and finally the X-rays and gamma rays. Okay, I'm going to spend very few words on these different portions of the electromagnetic spectrums. Just to give you some info, the portion of the visible light is the portion that our eyes, so our eyes, are able to detect. You might imagine that this is a very, very narrow portion of the electromagnetic spectrum, but this is the portion with which we are able to, let's say, to detect and sense the world, the world around us. Normally, this portion of the spectrum is divided by colors, and colors have, let's say, the double meaning of a specific wavelength range, and also, let's say, the color that we are able to detect with our eyes. Ultraviolet radiation, it's something that usually is not very is not the subject of normal remote sensing data, but just for information we mention here because as many of you might know, ultraviolet radiation can be harmful for our bodies. And fortunately, our atmosphere is able to absorb. I will talk about absorption in a few minutes. But so just with this slide, we can see that fortunately our atmosphere and our planet is able to absorb and so limit the major part of the harmful radiation for our bodies. The infrared region of the electromagnetic spectrum, it's a region that is usually detected by passive satellite images, and this it, let's say, brings information that also were exploited during this project. So the infrared region is a very broad, let's say, band, is very broad, and we can normally in a satellite we are able to process the near infrared and up to, let's say, the thermal infrared, that is more or less between the 8 micrometers and 15 micrometers. Infrared is also very important radiation because considering the temperatures of our planet's surface, normally bodies, let's say, or that have temperatures typical of our planet emit electromagnetic radiation in the infrared spectrum. So the infrared is something that is, let's say, very important also for the analysis of a lot of phenomena on the Earth's surface. Then we have the microwave range. I'm not talking about microwave because I'm not for sure that this has been already mentioned, but just to give you, this is the range of the electromagnetic spectrum exploited by the Sentinel-1 satellite. And it's useful to carry out very important tasks such as interferometry and so on and so forth. So when talking about electromagnetic spectrum, it is important to know that not all the whole spectrum can be exploited for satellite observations. This is because, as I mentioned before, for the ultraviolet portion of the electromagnetic spectrum, the atmosphere is a medium that is not, let's say, transparent for all the electromagnetic spectrum. So this means that only, let's say, some portions, namely the portions that are placed in the so-called atmospheric windows, are the portions that can be detected, can be, let's say, effectively used for satellite implementations. So that's, let's say, a very, very fast and dense introduction of the electromagnetic. But just to know, I'm talking about this because when we talk about passive satellite data and high-level services coming from this data, this is the source of the information. So this is the primary source of the information that we exploit. So at least it's important to mention this. So we're talking about the spectrum. Now we are going to talk about what is measured by a passive satellite. So we are going to introduce the so-called radiometric quantities. So radiometric quantities actually are used to talk about the energy. So talk about the energy that is emitted, the energy that is the incident energy on the Earth's face, or the energy that is detected by a satellite. Normally, at least for this very, very dense training, we can say that we deal normally with the fluxes and radiant intensities. So what is the difference between fluxes and radiant intensity is very simple. So The flux is actually it's power. So it's the power emitted by a source. And normally we do not measure fluxes, but we measure intensity. Why this? Because intensity is a more, let's say, easy to detect physical quantity, because it is, let's say, the amount of power per unit of area per solid angle, and it also depends from the wavelength. So from the portion of the electromagnetic spectrum that we detect. Just to give you some very few information, when we talk about, let's say, the interaction between this energy that we aim to detect with satellite, it is important to know that, as I already mentioned before, this energy is actually not, let's say, it is interested by a lot of different interactions. Namely, we can clusterize this interaction in 4 typologies. So we have transmission, reflection, scattering, and absorption. The interaction of the electromagnetic energy, so of the information that we need to detect, and the medium normally depends from the wavelength, so from the portion of the electromagnetic spectrum that we are going to measure, the incidence angle, so let's say from the geometry, just to use simpler words, and from the medium. Of course, the interaction between energy and the medium depends also upon the medium. So the transmission, when we have transmission, this means that the energy is able to, in some way, pass through the medium. It can have different optic interaction, but let's say the energy is able to pass through the medium. The reflection is the word itself, it's the reflection. So the energy actually is not able to pass, or only able to partially, let's say, penetrate in the medium, whereas the other part is just reflected away. The scattering is the reflection on not just one single direction, but is reflection on several directions. Absorption is a very, let's say, particular phenomena in which the energy, when hit a medium, is not able to, let's say, to leave, to go out this medium. It is absorbed, and what it happens then? It happens that the medium actually absorbs energy, and this normally is coupled with a transformation of this energy. So this energy normally is transformed in heat, and then the medium emits. I'm going to talk about this also in a few slides, because this is very correlated with the greenhouse gas effect. And so it's a very, very famous topic in these days. So, radiance. I mean, when talking about radiance, radiance is the quantity, the physical quantity that we are going to, that the satellite is able to measure. When talking about radiance, it's very important to stress the fact that, so radiance is energy, so is actually is a power for unit areas, for solid angle, and also for a wavelength. So it is dependent from geometry, areas, and detection technologies, and the portion of the electromagnetic spectrum. When talking about radiance, it's very important to understand that radiance is a physical quantity. So when we are going to deal with methods and, let's say, models that needs physical quantities, the radiance is the right information that we need to process. A different is the reflectance. Reflectance can be achieved by the radiance, but it's a dimensionless number. So it is a number that is not coupled with a physical quantity expressed in the international system of measurement. this is reflectance are, let's say, the suggested information to be used when carrying out, let's say, the calculation of vegetation indexes or classifications, because dimensionless number are easy to handle and are in such a way already normalized, is in such a, let's say, a normalized information. So it is a kind of information that is, let's say, the preferred one for machine learning or artificial intelligence implementation. So what is actually detected by a satellite? It's important to know that the satellites actually does not detect only, let's say, the reflected energy, but actually what a satellite detects is a very huge, is a result of a huge number of interaction between the sun, the energy emitted by the sun, the Earth atmosphere, the energy emitted by the Earth itself, and also the interaction between this energy and the atmosphere. So let's say the information that we process is, let's say, we process the information that is the result of all this number of interaction. But just to try, let's say, to show what are the possible interaction between the energy and the atmosphere, we can mention, let's say, as said before, the atmosphere is a medium, so is something that is in between that the satellite and the Earth's face, but it's something that it's able to influence the energy. Just to give you some figures of all the energy that hit the Earth's face, so that hit, let's say, our planet, only the 7% of this energy is reflected, and it's the portion of the energy that can be detected by passive satellite data. What does it mean? It means that, let's say, a lot of energy that that hit the Earth, actually it's absorbed by our planet. Why this? Because this is, I mean, just to talk about agriculture, it is a way in which, let's say, the biology actually specializes itself to get all the possible energy by the sun. And so this is also why the leaves are green, and why, for example, our eyes are able to detect, to sense just the visible spectrum of the electromagnetic spectrum, because this is, let's say, the portion of the spectrum that is, let's say, not affected by absorption. So this is just, let's say, to give you some insights on this. But what, let's say, causes the absorption in the atmosphere? Normally, we have, let's say, at least, this is a very, very limited list of gases that are able to absorb energy. The first two of them, so water vapor and carbon dioxide, are very, very strong greenhouse gas, because they are able to, let's say, absorb energy in the absorb the energy also in the infrared, and then to emit energy also in the infrared spectrum. So carbon dioxide, of course, is a very well-known greenhouse gas, but maybe not, it is not commonly known that also water vapor can have the same effect. The ozone is also is able to absorb, but it absorbs, let's say, the ultraviolet portion of the spectrum. And fortunately, it is a very, very useful gas for our health, because, as I said before, the ultraviolet portion of the spectrum is harmful for our body, especially for our skin. Of course, we can mention other gases such as the methane, but these gases are, say, limited portions, although also they are very, very strong greenhouse gas. So this is the concept that I expressed before. If the atmosphere is able to absorb gas, there are also portions of the atmosphere that are, let's say, quite prone to the transmission of the energy. So a portion of the atmosphere called atmospheric windows, in which the electromagnetic energy of specific wavelengths is able to pass through. As I told before, one of this region is the visible electromagnetic spectrum, and this is the reason why the life, at least the life on the Earth's face, is very, very specialized to get all the possible energy in this spectrum. Although this is not part of this course, but this, in my opinion, it's very an important information. Just to know, the yellow is also considering the temperature of the external part, the external layer of the sun, also the temperature related to the color, and thus the energy related to the maximum emission of the sun. So just to give you an idea that the whole life over this planet is, let's say, designed to get the maximum from, let's say, the sun. When we talk about the interaction between the energy, so the electromagnetic energy, and thus the information, I will tell this thousands of times, the electromagnetic energy is the information that we record and then we process, can be on different typologies, but normally it is commonly named scattering. So the scattering, as said before, is, let's say, that phenomena that in which the energy hits some particles in the or dry matter in the atmosphere, and then it is reflected in non-selective directions. We can have at least 3 different types of scattering, and this scattering depends upon the differences between the wavelength of the energy and the particles that are hit by the energy. So the Rayleigh scattering is when the particles are smaller than the wavelength of the energy. The Mie scattering is when the particles are on the same dimension of the energy, and the non-selective scattering is when the particles are bigger than the wavelength. What is the effect of the scattering? The scattering is unwanted when we process satellite images, and normally it also the scattering is also the reason why we need to correct satellite images from the atmosphere effect. We can say that the scattering can be highlighted with heights in satellite images, or in our life, the scattering, we can sense the scattering during sunrise and sunset when we see the orange or the red color of the sky. This is why this is really scattering, and this happens because the red is characterized by longer wavelength, and so when there is the sunrise or the sunset, the energy emitted by the sun actually is characterized by longer path because the inclination of the energy, and then all the radiation before the red are totally scattered, and so the longer wavelength are the ones that are able to pass through this process, and this is the reason why we have red and orange sky. Spectral signature. So this is now very important and probably more practically correlated with the activity of this project. Why spectral signature is important in this project? Because, as said before, the reflectance is the portion of the energy that is reflected by the Earth's face. And in some way, it's also the portion of the energy is correlated to the energy that can be detected by the satellite. Reflectance depends upon the wavelength and also from the material. So we can say that considering the electromagnetic spectrum, or just a portion of it, this is just a portion between 0.5 and 2.5 micrometer, can be characterized by how they reflect the electromagnetic information. So this let's say reflection can be so characteristics of the material that has been called spectral signature, because it's like a real signature of materials, and it's something that we exploit to carry out our analysis. So, for example, the spectral signature for vegetation is the one, is this one. So we can say that vegetation actually has not so much reflectance in the blue and red, and this is because actually it absorbs the energy from the sun, whereas the chlorophyll actually reflect the green, and this is the reason why we see the leaves as green. Then there is, let's say, healthy vegetation normally reflects a lot of information, a lot of energy, a lot of light in the near infrared. The water has, let's say, also another typical spectral signature. It is not characterized by high reflectances, and you can say this just by looking at a glass of water. A glass of water is transparent. This means that the light, at least in the visible electromagnetic spectrum, that is the portion of the spectrum that we can detect as human being, if it is transparent, it means that the energy is able to pass through. Whereas the water is almost a perfect absorber, so it absorbs a lot of near infrared and also SWIR information. So as I'm going to show later, water in near infrared is black. Ice snow, okay, they are white because they reflect a lot of information. They reflect a lot of energy in the visible spectrum, whereas the bare soil has, let's say, an increasing reflection with increasing of the wavelength. So talking about leaves, because actually we, in this project also, we produced a lot of vegetation indexes, so leaves are important. So what we can say that the leaves are able to absorb in the blue and red portion of the electromagnetic spectrum. They reflect the green because of the chlorophyll, and they also, because of their biological structure, are also able, when vegetation is in a healthy state, are also able to reflect the near infrared. Regarding the SWIR, so this is a spectral signature of vegetation, we can say that regarding the SWIR, the higher is the content of the water within vegetation, and the lower is the reflection in the SWIR. So this is a very important information, because as I'm going to show later, it can be exploited also to create vegetation indexes. So just very few words on the Copernicus program. The Copernicus program, I have to say we are very lucky because the Copernicus program is a huge source of information. It is a program that is, let's say, promoted by the European Commissions and owned by the European Space Agency, and it is component by the space segment, so the satellites that acquire the information, and 6 thematic services. So the six thematic services are the atmosphere monitoring, the marine environment monitoring, land monitoring, climate change, energy management, and security. So very, very fast. Of course, the slides will be available, and there are the links. So the atmosphere monitoring service is a service that exploits satellite data and in situ data, and restitute high quality and atmospheric composition information, surface emission and fluxes, solar radiation, and climate forcing. So information that are needed to carry out all the models for the atmosphere and also meteorology. Marine service is another service that that can be used for that exploits satellite data and in situ surveys. It has produced, let's say, information on marine safety, sea resources, and meteorology related to the marine environment. The land monitoring service, again, exploits satellite data and in situ information. It provides data for the monitoring of biophysical parameters, land cover and land use. These are a huge source of information from this sense. To also provide a thematic map on hotspot areas and reference images and data. And soon it will also be enriched with a ground motion service that is still under development. Climate change service is also another very huge source of information for our models. And again, it exploits satellite data and in situ surveys, and it release a very precious data sets on climate analysis, seasonal forecast, projections. So it is a very precious source of information that can be exploited also to design things like to carry out monitoring also in at the regional and the national scale. The energy management component has the task to provide timely and accurate information and to dealing with let's say emergency and humanitarian crisis. So it can be it can deliver on-demand mapping or services related to early warnings, whereas the security service is a service that aim to enhance the readiness and reaction to crisis, at least on these 3 fields. So borders surveillance, maritime, and sustain the European Union external actions. So very few words on the satellites because I'm on the Copernicus program, because I'm sure that they have been already mentioned in other sessions. So the Sentinel-1 is the active satellite, and it's exploited for especially for interferometry and land and sea monitoring. We also exploited Sentinel-1 in this project for classification purposes, and I will show you later how. Sentinel-2 also has been exploited in this project, and it has the possibility to support land and marine areas, and can be exploited for several activity applications such as agriculture, such as land cover mapping and time series analysis, just to mention some of them. The Sentinel-3 is another scientific source of data, and it's composed from four sensors. So the ocean and the land color instrument to detect in the visible and near infrared reflectance and information on chlorophyll and so on. Then we have the a radiometer to detect the marine and land temperature, a radar altimeter to detect to detect sea parameters like surface level and the wave height, and a microwave radiometer to measure the cloud's water content and thermal, let's say, and the emission of in the thermal radiation. Sentinel-5, 4, and 5P, that is, let's say, the precursor emission, will be implemented for the monitoring of atmosphere parameters, such as, let's say, dangerous gases if present in a high concentration. And for example, the 5P mission has a payload called the tropomi sensor that is able to sense the Earth surface at 7 square kilometers in order to deliver information about the concentration of this gas that we show that are shown in the slide. Whereas, lastly, the Sentinel-6 is the last born mission in the Copernicus program, and it will be made on 2 twin satellites that we with aim to detect information related to sea level, wave height, and ocean winds. Of course, this is a very, very small introduction on the Copernicus services and data. Lots of information and insights can be found on the Copernicus websites and also on the Copernicus courses and the information materials. And a link is provided in this slide in order to give you the possibility to easily find all this information. So we are approaching to, let's say, the final part of this introduction of remote sensing, and I'm going to talk about vegetation indexes. Vegetation indexes are part of, let's say, of this cluster of technique called image enhancement. So why we need image enhancement? Because normally satellite images and the information that we record should be, let's say, processed in order to extract the information that we need from them. And so vegetation indexes is one of the possible ways to do this. Vegetation indexes exploits normally the spectral signature. So they are designed in order to exploit the shape of the spectral signature. I will tell you later how normally. And in their initial, let's say, formulation, they normally are of course application dependent, and in their initial formulation they were just, let's say, band ratios. But now we have, let's say, more complex vegetation indexes. And just to give you some example, in this project we produced 7 vegetation indexes. So the first one that we produced is the normalized difference vegetation indexes. That is probably the most famous and well-known vegetation index. It is calculated starting from near infrared and red, and I will show you later why. And it is expressed in a range between minus and +1. Negative values of NDVI corresponds to water, and values close to 0 are related to bare soil or with, let's say, senescent vegetation. whereas higher value, close to 1, are related to very healthy vegetation. So this is a density slice representation of NDVI. We can see here that the water normally is black, whereas in this representation, let's say the healthy vegetation, the greener is the picture, the better is, let's say, the condition of the vegetation. Another index is the anthocyanin reflectance index. This index is specialized to, let's say, detect spectral kind of pigments that can be detected, exploited normal passive satellites, such as the Sentinel-2. It is usually used for, let's say, high plantations, and it exploits the green, the red, and the red edge. So the green information and the red edge, that is that very, very narrow portion of the electromagnetic spectrum between the red and the near infrared. And this is a portion characterized by a very, very steep increase of reflection from vegetation. This is another representation of an index. This is a gray scale representation in which the white is very high value of this index, and again the black is very low value. The enhanced vegetation index is another index that has been designed to, let's say, to deal with some limitation of the NDVI. So the enhanced vegetation index is normally proposed in area with very high leaf area index, and it exploits 3 different bands. So the near infrared, the red, and the blue. Here again, we can see a representation of this index with let's say, the greener area related to very dense vegetation. Whereas the normalized difference moisture index is another normalized index that exploits the information from the near and the shortwave infrared band. So this information is sensitive to the water content the moisture of the leaves, and can be also exploited as a proxy for the, let's say, the healthy state of the vegetation. Because, as I showed before, when leaves are have water, so are, let's say, in a good state, are not dry, they absorb the water inside the leaf, is able to absorb in the swir region. This is another representation of the swir. Here we can say in blue the region with high NDMI and NDMI areas. Then there is also the normalized difference water index that is exploited in the area infrared and the green, and it's used to map water bodies. But I have to say that this index is not very, very precise, and it can, let's say, results in some false positive, especially close to built-up areas. The soil adjusted vegetation index is another empirical derived vegetation index. Actually, it is an index that has been designed to improve the NDVI in order to let's say, accounts for the effect of soil color and soil moisture and so on. So it exploits, again, the near infrared and the red, but it also needs some theoretically empirical parameters that should be calibrated in each application. This is a representation of the SAVI. And lastly, the leaf area index is another index. The leaf area index is a dimensionless index that simply measures the one-sided green leaf area over a unit of length. To be honest, the detection, the retrieval of the leaf area index is not a solved problem for the Earth observation community. So there are different techniques to detect it. For example, the ESA SNAP software produced the leaf array index with a neural network regression. There are other retrieval techniques that exploit, for example, physical laws, like empirical physical laws, like the Lambert-Beer and in DVI. In this project, we exploited the results of the SNAP ESA project. So, just to mention some practical tips for the creation of new, let's say, spectral indexes. Normally, when we, I hope you can see my my mouse. Probably okay. So now, yes. Normally, when we need to design a new vegetation, a new spectral index, we should start from the spectral signature of the material or of the plantation of the things that we should like to detect. It's very important, and this is something that it's done in every normalized difference index, that we should be able to detect and exploit the shape of the spectral signature, and in order to define this index starting from the peak of the spectral signature and the lower portion of the spectral signature. The higher is the difference, so between these 2 points, or this point in the near infrared and this in the sphere, and let's say the higher is the dynamic range that the index is able to capture, and so to represent our to represent, let's say, the information that we would like to detect. So this is the technique that is actually implemented for example, for the creation of the normalized difference vegetation index, or the normalized difference. So the normalized difference vegetation index exploited this peak and this other, let's say, depression of the spectral signature. The normalized difference moisture index exploited this peak and this depression of the spectral signature, and so on. So this suggestion can be exploited also for, and in scientific literature is usually the starting point for the definition of every new vegetation index. So this is, let's say, the end of the first part of this training, and related to, let's say, the introduction of passive satellite data. I'd like to ask you if there are any questions, so I will be glad to answer them. And before, let's say, to start the session related to the live presentation, so to the presentation of the platform that we exploited for this project, and the result focused session. So, are there any questions? Hello, can you hear me? I'm sorry, can you hear me?
Yes.
Okay. Okay. So, if are there any question, I can answer now, or maybe in I can answer question in a later stage, maybe related to the activities carried out in this project. So, let's start talking about the activity carried out in this project. So just to be sure, in 30 minutes, there will be the break. So in this project, we, as Planetech Italia, let's say, worked for this specific topic for the production of analytics related to vegetation indexes and the production of land use maps. In particular, the selected areas were agreed with the stakeholders, and we used the tiling system of the Sentinel-2 satellite in order to detect them. So we produce this data on the Caro district, on the Ende district. So we produced both vegetation indexes and land cover maps on this, and also on the Chanjur district. So why why, let's say, it is interesting to produce analytics and land cover maps? Because actually Earth observation technology can be a diagnostic tool and serve as an early warning system, especially for, let's say, the monitoring of wide areas. I'm not trying to say that Earth observation should totally replace the ground, let's say, sampling campaigns, but it for sure also with exploitation with open data, so remote sensing, it's for sure, let's say, a huge source of information that can help in the decision-making process and, let's say, in the optimization of our analysis. The potential of the Earth observation, so also Sentinel-2 and also satellite, but also active satellite for the agricultural sector, to be honest, is still in let's say mid-early stage, in the sense that differently with let's say interferometric technique that are, let's say, very well I mean, interferometry with SAR data is a very mature technology. With agriculture, we can't say that exists a one-size-fits-all, let's say, application. So the application of remote sensing at agriculture should be needs the collection of requirements by the user, and then the development with, let's say, an agile and a co-creation process between the technicians and the stakeholders of application that, let's say, are really needed for the community. So in this project, we exploited the Copernicus Sentinel-2 data for the calculation of vegetation indexes. The observation period includes the years 2020 and 2021, and the analysis is restituted in a parcel-based representation. Why this? Why parcels? Because parcels are, let's say, a way that is suggested in order to let's say have to enclose within a geometric entity, a geometric shape, so named parcel, the information that is inside several pixels. So in order to be able to see an information that is more robust and not affected by noise that is usually present in pixel analysis and let's say the salt and paper effect that is usually present in especially when we deal with, let's say, higher spatial resolution. We produced just to demonstrate let's say, the capabilities of these techniques, two different analytics. So the difference, so for each index, we produced the difference between, let's say, a specific quarter of the year and its previous quarter of the year, or the difference between a quarter of the year and the average value of that quarter in 2 years. So the method exploited for the calculation of the analytic is, let's say, shown in this slide. So we started from the area of interest, so from the Sentinel-2 tiling system, and from the land cover. I will talk about the land cover later, and from the hexagonal grid. Here the area, it was the preliminary value, but we implemented that different area just to, let's say, to demonstrate for demonstration purposes. So we downloaded the data, and I'm going to talk about the download of this data also in the last part of this training related to semi-automatic classification. We calculated using our software pipelines the 7 selected indexes, the ones that I presented before, and then we calculated the average value for each of the index. Of course, we applied some filtering and some, let's say, conditions in order to do this, because in order to preserve, let's say, only the meaningful information. And then we also apply, let's say, we exploited the information coming from the land cover map to represent the vegetation indexes analytics only for the, let's say, the areas classified as cultivation, paddy fields, and tree crops. And then we restituted, so we created the final analytics, and we classified them in decreasing, stable, and increasing. So I'm going to show you a video on the Reticus agricultural platform. So just to okay, just to so we provided, of course, let's say, the access to the platform will be, as agreed, it will be given after the end of the training. And the platform starts from, of course, a login page. And after the authentication, we can select. So there is the loading of the different maps and the loading of the different analyzed areas. So that in this case, the 3 districts. So Karo, Chanjur, and Ende. By clicking on each of the selected area of interest, we can launch the app, and we can, for example, see what are the indexes already loaded in the platform. So we can launch, for example, the NDVI index. So we have, let's say, the loading of the data and the loading of the area of interest with all the parcels related to the selected area. So we can see that we have a we can see that we have a pie chart that is able to show the distribution of the different value of the classification in stable, decreasing, and increasing analytic for the specific area and for the specific index. Then we have the possibility to select the specific analytic, so the difference with the previous value related to a specific quarter, or the difference between the seasonal value expressed in percentage. Of course, the pie chart is an interactive pie chart, And by clicking on a specific portion of the pie chart, we are able to highlight only the section, for example, of the increasing, the stable, or the decreasing area. By clicking on this button, we are also able to access to the other layer. For example, the Reticus Agriculture is equipped with different base maps. The default base map is the OpenStreetMap, but we have also other base map like the Here Technology base label map or the Here Technology aerial map. By clicking, of course, we have also the possibility to query the single parcel, and we can have the possibility to access to all the information within these parcels that is related to the class. So if we have stable, decreasing, or regarding to the different, let's say, quarters, we have also the amount of the different land cover and land use in every single parcel. We have also the possibility to have the same values for the difference with the season indicator analytic. And we have also the values of the index, that in this case is the NDVI for each of the quarter. So we have for each parcels a very, very dense information. But again, I would like to stress that this is just one of the many possibilities of this kind of application that can be customized according to the user needs. So another important source of information, for example, is also this panel with this table in which we have the disaggregation of information for each indicator, and express it also in consideration of the different land covering classes. So this, for example, is a useful source of information in order to talk about to create reports and to, let's say, to highlight how let's say it is the general trend on the monitored areas. And for example, here we can see that for 3 crops there is, let's say, 25% of decreasing with regard to the seasonal volume of this specific quarter of 2020, and so on and so forth. So this is again one of the possibilities that can be released by this kind of application. And of course, they can be also customized if designed to, let's say, release information at different areas level and at the local, regional, or national level. So we have, as I told before, the breakdown of the different classes. And we can have we can get insights on the different indexes and how they are distributed over the crop areas. Okay. So we have prepared another video for the Chanju district. For example, here we are going to show the normalized difference water index. So an index that it's able, it is able to detect the amount of water in the area. Again, we have the possibility to select all the difference indicator and the possibility to have a visualization only related to a specific class. So at a specific class of indicator related to the decreasing, stable, and increasing behavior. Also in this case, we have the possibility to change the base map according to our needs and to show all the metrics related to each parcel. We have the possibility to see it here that the paddy field class is the one interested by most of the changes. This means that paddy field is, let's say, a very common here. So we can see how the system is able to handle this information. And okay. And we have prepared also for you another video to show, for example, in Caro, the leaf area index. So here we can say that we have also a portion of area in which there is no info. So this means that in this area, after the application of the filtering procedure that we applied in order to collect only the areas with meaningful information for the leaf area index, we were not able to find these. These parcels were characterized by a quality of information that was not suitable if compared with the dimension of the parcel. So it was excluded by the analysis. So again, for each index, it is possible to have a clear idea, a clear picture of what we are seeing. We have the possibility to show for each quarter and for each analytic the differences and the distribution. We are going to select the decreasing, stable, and increasing classification. And again, we have the possibility to have, let's say, a very synthetic overview of the distribution of the different classes over the three selected land use and land cover areas. So again, this is an information that can be used to create reports or to let's say define actions, strategies, policies, or let's say other kind of intervention. Of course, but this is, I mean, again, this is obvious. Our platform has the possibility and the flexibility to change its base map. And you see, there's a nice user experience and the possibility also to query the single parcel. We can see you can see that our this, as I told before, this area has been the area in which we calculated the analytics was the area related to 3 land cover classes, whereas these holes are related to other classes, for example, built up areas or tree covered areas and so on and so forth. So these holes derives from the data fusion between the land use and land cover map that we produced and that I'm going to show later, also from an algorithmic point of view, and the indexes calculated. So this is another nice example of how to exploit this information totally derived from Sentinel-2 and Sentinel-1 satellite data. Okay. So for, of course, in these slides, we also prepared, let's say, we also give some infos on the things that we have just seen on the videos. So we have it's like I say, we provided like a tutorials just to have a recap of all the functionalities. So the possibility to select the different area of interest agreed in the first phases of the project together with the stakeholders involved, and to start the application by selecting a specific vegetation indexes. We always have a clear pictures and a clear overview of what we are, let's say, of what the screening is showing us, and so what the platform is showing. We have the possibility to select the different indicators that in this specific case are related to an analysis of just 2 years. But as I said before, this is just, let's say, not a limit. This is just, let's say, what we were able to deliver in this very, very small demonstration case. But it is not, it is, let's say, very common also to produce analytics that are based on very, very of longer time series, and not on a quarterly scale, but also at a weekly or monthly scale. So see, this is the possibility to customize this according to the user's needs. Also, the classification, let's say, of the analytics in the decreasing, stable, and increases, this is just one of the possibilities. So we, let's say, for demonstration purposes, we implemented this, let's say, schema, but this schema is something else that can be agreed with the stakeholders, or can be also the outcome of other models applied in, let's say, a processing pipeline. So let's say this is very scalable and can be really customized according to user needs. The pie chart again has the possibility to show the differences between the classification in stable, increasing, and decrease. Of course, if we had different classifications or different indicators, the pie chart or other, let's say, business intelligence pop-up can be customized to feature other information. we have the possibility to deliver with this platform also, let's say, synthetic informations, very useful to for report or to have, let's say, a synoptic view of all the of the overall status of our monitored area. So we can, let's say, this can be a very easily dashboard to use to have a look to what is, for example, in a decreasing stage. So I might imagine that if the decreasing is an unwanted effect, for example, here we can see that we have, let's say, for general cultivation, a 4% of decreasing. So we can use this information to look for these areas and to maybe to take some actions to correct this. So this is very important. And again, there is the possibility to create dedicated pipelines that can do this also in an automatic way. And it is very, we can do this, or it is also possible to couple this with phenological models and so on and so forth. So to link this information to specific cultivations. Or to make this cultivation specific. Again, the platform has the possibility to also query, so to see the information inside the single parcel. And this is, let's say, a useful information if we are interested in a specific area. This is a very fast way to have access to this information and also to see what is happening on these areas. And that's all for, let's say, the live session, or at least, let's say, the presentation of the Reticus Agriculture. So Nancy, if I'm not mistaken, now is the time for the break, but if there are some questions, I will be happy to answer them.
Yes, Novelli. We have one question, I think, in the chat box. It's from Bada Slaman. So would you like to answer first before we go into a short break?
Yes.
So the question is, he would like to ask you if we would like to produce the change macro condition map using Sentinel-2. Which one is best to use? Is it NDVI, SAVI, or MDVI, or we better use all of them rather than just one of it?
This is a question that let's say has not a single answer, because when it is important to understand what is the subject of the change detection that we are interested in. If we are only interested in, let's say, the decreasing or increasing of the area covered by mangrove, so a good land use and land cover map product probably might be the best option. So it might be, and the best option, and can be also exploited to carry out not just the detection of this specific land cover, but also other land cover. If our purpose is not only related to, let's say, the detection of increase or decrease of the covered area, but this specific class, the exploitation of vegetation indexes is useful in order to have insight on the phenology of this, let's say, vegetated area. Regarding the specific index, I have to be honest in telling you that in most of the case, the indexes that feature the same spectral bands as input are highly correlated. This means that they deliver very similar information. So, for example, I will not suggest the exploitation of NDVI and SAVIT, but maybe I would suggest the exploitation of NDVI NDMI, so of index that feature and enhanced vegetation index, because this index are, let's say, created starting from different informations. So you can get, let's say, the same phenological behavior, but under three different point of view. And so you can have, let's say, create a model, or let's say a decision algorithm that is able to detect the changes that you are interested. I hope this answers the question.
We would like to invite Mr. Bada Slamet. Is it the Antonio answer satisfy you?
Sorry, can you repeat, please?
Oh, I'm sorry, Antonio. I'm asking to Mr. Banda.
Okay.
Yeah.
Okay. Sorry. My hair.
Yeah. I would like asking with bahasa. Kepada Bapak Banda Slamet, apakah I think he's still here, but Bapak Banda? Okay, maybe we can waiting him in the chat box. So may I continue this session? We will have a break for 10 minutes and we will come.
Oh, okay. So in 10 minutes, I will be here again. Thank you.
Thank you, Antonio. Bapak dan Ibu sekalian, kita tadi sudah mendengarkan penjelasan dari Antonio. Dan kita akan rehat sejenak selama 10 menit. Kita akan kembali pada pukul 2:44. Ya, terima kasih. Baiklah, Bapak dan Ibu hadirin sekalian. Sekali lagi kami sampaikan selamat bergabung kepada Bapak, Ibu, serta rekan yang saat ini telah terkoneksi melalui jaringan Zoom Meeting dan menyaksikan kegiatan dari hari ini melalui kanal YouTube channel PUSFATJA LAPAN. Kembali kami sampaikan bahwa acara ini disiarkan secara bilingual dan bagi Bapak Ibu yang mengikuti melalui Zoom bisa mengartikan fasilitas interpreter untuk memilih bahasa yang digunakan dengan memilih tombol di bagian bawah layar Bapak dan Ibu. Bapak dan Ibu, marilah kita lanjutkan kembali sesi pembelajaran ini. And we would like to invite you again, our colleagues from Planetech, to continue our session. So I offer this time and screen to you, Dr. Novelli, and we would like also remind you to have a second break or for 10 minutes at 4 p.m. And now the time is yours.
Okay, perfect. I'm going to share again the screen. Thank you very much, Nancy. So, can you see my screen?
Yes, perfectly.
Okay, perfect. So in this 20 more or less minutes session, I'm going to show you other examples related to the analysis carried out by Planetech Italia for this project. So we are going to show over the 3 different area of interest, some, let's say, insights that can be achieved using the analytics, and also the restitution of the land cover and the land use maps. Then after this, let's say, a result-focused presentation, I'm going to talk about, and I hope this will be very, very interesting for the many of you, about the algorithm that we implemented for the classification of the land cover and land use map. So, and I hope to receive a lot of questions on the classification. So, as I told before, we produced also the land use map on the different, let's say, on the 3 different areas, and we this is for example the land use map related to the Ende district. So we can see that we have the majority of the area covered by trees. We have also here some paddy fields, and again we were able also to detect the settlements and other classes such as savanna and shrub. This is, for example, a subset of the Ende district extracted from an aerial map, and this is the classification result for achieved here. We can see that the majority of the area is covered by 3 crops. We have some paddy fields and let's say general cultivation in the other part of the area. Regarding the indicators, we also provided let's say the data, so the vector data, the shape files in this specific case of the indicators. If, for example, we consider the difference with season indicator, that is the percentage difference of the vegetation index values at a quarter and the values of the same quarter on the previous 2 years, the indicators is expressed at 1 hectare cell level and has been calculated for the 7 indexes, so for NDVI, ARI, Enhanced Vegetation Index, and so on. For example, this is the zoom over this area, and we can see that for the normalize different vegetation index. We have, let's say, for the difference indicator between the Q2 of 2021 and the average value of Q2 of the whole period analyzed, we have more or less a stable classification, whereas we have some decreasing areas and a few percentage of increasing area. So we can say that we can exploit this indicator. Also, of course, we can zoom over specific areas. We can look for the area that we are specifically interested in, and let's say start with some analysis. We can, for example, select, if we hypothesize that in this area we should not have, let's say, decreasing cells, or at least we should not have areas that feature always a decreasing trend, we can exploit the information provided from the geoanalytics to detect where are placed areas that are featuring, let's say, a continuous decreasing trend. So this means that these areas are characterized by a loss of biological matter and a decreasing of an NDVI. For example, we can, with a single query, select all the area that feature a decreasing, and these are the selected areas, again, in this specific subset. We were also, we would like also to show you that the selected areas are also can be detectable, that this information can be exploited also in combination, for example, with Google Earth time-lapse functionality, and also it was a sort of, let's say, of validation of our analysis in order to understand if even a cell of the, so a parcel of the area of 1 hectare is able to represent this kind of trend. So, for example, this is a video that we acquired over these specific 3 parcels, and you can see that from 2019 and 2021 we actually have a detectable decrease of green in this area, this and the trees, and this is actually something that it's, let's say, a very practical visualization of what this geoanalytics, or what time series geoanalytics can deliver to us. So this is just, let's say, as I stressed before, just a very simple example that let's say we proposed here, just to show what can be at a first glance their expectation. But consider that since this is an information that achieved with a query, we already know for sure that in these areas the decreasing pattern is confirmed, and so we could also exploit the reliability of this information to also, let's say, create alert systems, or systems that, let's say, can send us notification with regard to these specific areas. In this project, we didn't do this because, I mean, there was not the possibility to develop, let's say, such, let's say, robust system, but we had just the possibility to, let's say, to show what is, let's say, what are the potentialities. But just to mention that this is something that is feasible, and it's something that can be done exploiting just satellite data. You can have a system that can send you alerts and notification with regard to your area of interest. So let's go over the Karo district. Again, this is the land cover and the land use map. You can see this is, I have to say also, this is very a visually appealing map, because land cover map, I have to be honest, are always, maybe I'm, because it's, because my background, but I mean, I always find very, land cover maps, let's say, are beautiful to see. And here we can see that also in this area, we have, let's say, a good percentage of tree crops and tree covered areas. We can conclude that a lot of the major part of the area is covered by trees, and these trees are, let's say, can be managed by are managed by these agricultural owners, or are just belonging to forest. Again, here we were able to detect settlements and, of course, water covered areas and so on and so forth. So this, for example, is again a subset of this specific area. We can see this is an area highly in which the presence of the human activity is very, very high. And as you can see, our algorithm, our classification algorithm, was able to detect that this is an area that is, let's say, related to human activities such as cultivation, paddy field, tree crops. Here we see a whole, and of course this has been classified as urban settlements. You can see here this is in red. Sorry, this is in red. So you can see here the classification algorithm performed it quite well. Okay. Again, we are going to show the same application with in the Karo district with the DNDVI, and again with just to show an example, one of the main example that might be, say, produced with this data. So the example with the S indicator, we selected again a subset of the whole classified area. You can see that the major part of the area is interested by human activities, because this is all area interested by crops and of different kinds. We can see that we have also in the subset, I would say, a not balanced in distribution of the increasing, stable, and decreasing. We have for Q2, the majority of the area is interested by the increasing, so an increment of the biomass. This actually, considering the season, can be just a confirmation of the fact that crops are in their growing season and that they are, let's say, producing biological matter that is detected by the satellite. Again, in this sense, in this case, we can see that there are stable and decreasing areas. So, but stable and decreasing areas over cropped areas, is this something that is expected or not? So this is, for example, another exploitation of this data. So we can select a subset. We should know what, let's say, we should expect, and we can notice that we have a strange behavior. So strange behavior in agriculture can be, let's say, related to a very wide range of different reasons. It can be for pests, it can be for, let's say, some damages on irrigation systems, or other kind of, let's say, an erroneous implementation of fertilizer or something, something similar. Sorry. And again, we can select we can select all the areas that are featuring a continuous decreasing trend. That's just because we might be interested in those areas that for strange reasons in a subset in which we expect the presence of cropped areas. It's strange to see areas that are featuring a continuous decreasing trend. So what this means, probably these are areas that are affected by land degradation. There may be several reasons, as I told before, but this can be, I mean, we might not have the possibility to have, let's say, people in every corner of our monitored areas. So remote sensing is a very cheap and convenient way to have this information. And again, in my opinion, this is a very valuable source of information if we detect that there is a decreasing trend over cropped areas. This is, let's say, something that we called okay, sorry, this is another video that we created here to show how but I don't know why it's not working. Okay, so you can see here that it's strange. So this is a strange behavior, and maybe there might be some problems in this area, and this is a tool to detect this problem and to identify how there is the need to let's say put in place more resources and to see what is actually happening in these areas. So this is, in my opinion, a very valuable source of information. And again, we can propose this same schema also for the Chanjur area. Here we can see that we have a high amount of paddy field cultivation in this land cover area. We have tree cover, a good amount of tree cover, and we were also able to detect settlements. Again, this is a subset with tree covered areas and paddy field. And we can see that our algorithms, again, was able to distinguish between natural tree covered areas. These are obviously natural tree covered areas and areas that are characterized by human activities. Again, we can see the indicator regarding the difference between the seasons, and we can see here that we have for the Q2 a predominance of decreasing pattern. And again, this might be, this is not in principle a problem, but it depends on the knowledge of what, let's say, is over what is the specific crops. So this is an information that should be always, as I told before, in agriculture, there is not a standard way. We should couple this information with other information, for example, coming from land cover, but also coming from other national observatories or national databases. So we can, for example, expect that during Q2 here, the decreasing should be the expected behavior. So this is normal, but if this is not normal, then this area is featuring some problems. And again, this is a tool to show, to detect areas in which this problem is particularly present, such as the areas in which the decreasing trend is constant. More than constant, it's always present, let's say this. So this again is the same exercise of highlighting areas with the decreasing trend. And again, we tried to cover, to show with a time lapse this for 2020 and 2021. This is the area. We can see that there is a, let's say, a general, I would not say degradation, but let's say that visually the area is featuring a loss of vegetation. So why this is happening? Earth observation can't say you why this is happening, but Earth observation can tell you this is happening, and can tell you this is happening in this period. So you have the possibility to take action or not. So we, let's say, this is the end of the result-focused session on the geoanalytics. Again, it is important to stress that this is a demonstration. With the possibility offered by this project, we were able to demonstrate this, but several other things might be put in place if, let's say, designed and agreed with stakeholders. So if you have specific questions on this part, I will be glad to answer them. I don't know, Nancy, if Nancy, are there any questions, or I can?
I'm monitoring in the chat box. There have not question
Okay.
yet. Yeah.
Okay, good. So this means that we can. I hope this will be also another very interesting session, because I'm going to talk about the algorithm that Planetech Italia implemented for the production of land cover maps. So in this project, land cover maps have been used not only for the production of land cover maps, but also this information has been, let's say, exploited for the calculation of the geoanalytics. If you remember some some slides before, I've showed that the geoanalytics were calculated and they were characterized by holes. I mean, not all the areas were covered by geoanalytics. This is because we exploited the information extracted from the land cover and land use map to calculate the vegetation indexes and thus the geoanalytics only on those areas that were classified as cropped areas, so areas interested by cultivations. So, and this is also another example, totally Earth observation based, so we didn't use other ancillary data, other, let's say, external source of information apart from the collection of training data for the classification to achieve this result. And this is, again, is just, let's say, important to stress that all these results have been produced exploiting open source data, so data that are free of charge and produced and made available, so from the Copernicus program. So this is very important, because without all this hub data abundance, we would be not able to produce and to show this result. So let's start. I do hope that this will be interesting. The algorithm, for the production of the land use map, we created an algorithm that is able to process optical data, so Sentinel-2 data, SAR data, so synthetic aperture radar data, and this Sentinel-1 data. Then these data are, of course, pre-processed, because I mean, we can't use data as they are in a classification algorithm. We should, first of all, guarantee that these data are fused, are merged in a, let's say, a data structure that can be, let's say, ingested in a classification algorithms. Then, in a parallel way, there is the collection of the ground truth And this is why I've called this algorithm semi-automatic, because if we have the need to collect ground truth, I mean, there is still the need to exploit the manual collection of ground truth in order to feed and train the classification algorithms and in order to achieve the good results. Then after the creation of the data framework, so of the two data and of the optical and SER data and the collection of the ground truth, finally it's possible to train classification algorithms and to achieve as output data a land cover map. And then, of course, there is the need to validate this data or to exploit this data for further post-processing steps. For example, as I mentioned before, a further post-processing step might be also the ingestion of this land cover map in another processing pipeline, like, for example, the geoanalytic pipeline or a pipeline for a decision support system. So let's start to talk about the pre-processing. I have to be honest. When talking about classification and whatever classification is, never underestimate the pre-processing of the information and the collection of the ground truth data. I have to be honest, these two steps are the most time-consuming one. The classification, in most of the case, is, I'm not going to say that is the simplest one, but the classification normally exploits, let's say, literature and algorithms, and it's something that can be coded. Here we have the need to collect data, to pre-process data, and to guarantee that this data might be ingested in this algorithm. And this might be a time-consuming task. So if you are designing certain kind of application in which there is the implementation of artificial intelligence or machine learning algorithms, never underestimate the time effort to do this. It's very important. Of course, in this project, Planetech Italia has already a wide experience in these tasks, and we were able to probably design all the timing and to do this. But in my experience, I had, let's say, several students of thesis, of master degree thesis, and other master thesis, and most of the times I realized that many of them underestimated the task of training and pre-processing. So let's start with the collection of Sentinel-2 data. In this specific project, we ingested the information enclosed in 1 year of Sentinel-2 data, but we didn't collect the 1 year of Sentinel-2 data. Rather, we exploited a service that's called the Sentinel-2 Global Mosaic Service. That is one of the service enabled by the Copernicus Land Monitoring Service to create a mosaic surface reflectance product derived from Sentinel-2A and B platform. So the service, the Sentinel-2 Global Mosaic Service, is able to generate mosaics and is able to create a radiometrically normalized information, so composites. What this means? This means that if you try to put to mosaics Sentinel data, Sentinel-2 data, or passive Sentinel-2 data, normally, even if those data are atmospherically corrected, they are already singularly normalized and let's say enhanced at the best of your possibilities. You will notice that if you produce a mosaic, you will have discrepancies. between the radiometry of this data. Why we have this kind of discrepancies? Because actually we can have different atmospheric conditions that might be not completely removed by the atmospheric correction algorithm. We might have a slight differences in sun incidence angle. We might have also other, let's say, local artifacts due to the specific meteorological conditions. So you need also further pre-processing steps to do a proper mosaic. And this service is able to deliver, let's say, a reasonable quality of mosaics. And for this reason, we exploited this service. Coming back to this, to the Sentinel-2 satellite. Sentinel-2 satellite is a satellite that is able to deliver 13 bands. We exploited only 6 out of 13 bands, namely, so the band 2, 3, and 4, so the blue, green, and red band. We exploited also the band related to red edge and so vegetation area, and the SWIR band. This choice was made since, let's say, we were interested in, above all, in the selection of bands that were most sensitive to vegetated areas, and let's say, and in the differences between vegetation and water. Indeed, we included on purpose the band on the red edge and also the SWIR band in order to have this information. We also exploited other source of information. We are still talking about the pre-processing of only the satellite, the Sentinel-2 data. We exploited the metadata offered by the Sentinel-2 level 2A product, so the metadata that are related to the bottom of atmosphere Sentinel-2 product, to remove clouds and other artifacts. This is a very important feature of the Sentinel-2 data, because you can exploit this information as the starting point to mask out all the areas that are affected by clouds, high snow, or other artifacts. This is very important because without the presence of this metadata, you should develop your own detection algorithms, and then you should implement in your processing pipeline. Sentinel-2 data makes this, let's say, simple, because it delivers already this information, and you can decide to exploit this information as it comes, or you can decide to merge this information to have, let's say, a more complex masking pre-processing algorithms in order to be sure that only the meaningful information is processed by your classification algorithms and or your artificial intelligence application, and not, let's say, information that comes with a bias deriving from clouds, haze, or other atmospheric problems. Regarding the Sentinel-2 data, we not only considered the original bands, but we also considered the other, let's say, synthetic information. Why I call this synthetic information? Because, let's say, when we talk about vegetation index in phenology, or with let's say, people that are expert in agronomy, we are talking about something that is related to biomass, to phenology, and so on. But when we are going to exploit this information in an artificial intelligence procedure, or say a general machine learning or classification algorithm, This information are just, let's say, new informative layers. These are informative layers that we create and with one specific purpose, that is to provide an informative content that is very, very sensitive to vegetation. So in some way we are, let's say, cheating in a sense that we are producing a new bands, so new input data for the classification algorithms, starting from the original. So starting from the original data, in order to have, let's say, the possibility to include more information on vegetation area. This is very, very important, and I can tell you that the generation of this synthetic information, so I call this synthetic because one might argue, okay, but you are using the same band that are already present in the data. Why do you need the creation of this, let's say, new information that is derived from information that is already ingested by the algorithm? The reason is why, because it is demonstrated by the scientific literature that the adding of these new informative layers, of a limited number of informative layers, even derived from information already stored in the original data, actually has benefit, features benefit in the classification outcome. Of course, if we, let's say, propose to include, let's say, 5 different NDVI calculated with the red edge band, or I mean, we can do this. This is not useful because, I mean, here we are adding redundant information. But when we, a rule of thumb to be sure to do, let's say, that the right thing is to at least consider indexes that are different. In this case, where are the differences? Here we have the sorry, here there is an error. It is NDMI. So here we have the NDVI that has the near and red band. We have the NDMI that has the near and SWIR band. So we are sure that we are adding 2 indexes that are different because are, let's say, focused on different aspects of the spectral signature of the vegetated area. So if you remember, in the first part of this training, I've shown you that these normalized difference indexes are created just to take advantage of the shape of the spectral signature of vegetation. So here we are considering the different portions of the spectral signature of vegetation, and for this reason we can be rather sure, and this can be also demonstrated numerically. I'm not going to do this now, but this can be demonstrated numerically, that adding these 2 indexes has, let's say, a positive effect on the final outcome. Whereas adding this is an index that is, let's say, similar to the NDVI, but this has some empirical corrections. So this is an index that is optimized to take into account the soil moisture and, let's say, contributes on the vegetated area in order to improve, let's say, the capability to discriminate between them. So this is the pre-processing for the Sentinel-2 data. So we downloaded the stack of the radiometrically normalized and merged data from the global mosaic service. We then applied a masking process to remove the areas that are affected by atmospheric artifacts or by clouds or by, let's say, other artifacts that might affect the performance of the classification. And then we produced synthetic information. So we produced more information starting from the original mosaiced data, so starting from the Sentinel-2 data, to improve the outcome of the classification. However, this is not enough in our opinion, because if we have the possibility to exploit also another source of information, such as the one provided by ActiSensor, why we should take advantage of this. And in our processing pipeline, we also included active remotely sensing data to the classification algorithms. Why we made this? There are several reasons to include radar data in a classification algorithms. This is not the usual. It is not the business as usual, but let's say radar data is another informative layer. It is a layer that for sure is not very correlated with the information provided by the optical data. And when in information theory, when we are dealing with machine learning algorithms, if we are able to ingest the algorithms with information that is not correlated, we are doing the right thing. So we are providing information that is really useful to get insights in our area of research and information, and we are avoiding to do one of the most important mistakes that is usually can be done in the application of these algorithms. That is the ingestion of the redundant information. As I was telling before, it's very easy to let's say introduce redundant information and I would like to say not useful information, because if we have very high correlated information, this means that we do not need too much information. We just need one single informative layer, and we can avoid the selection and the exploitation of other informative layers that are correlated, because if we just correlated information, this means that we are just, let's say, overfitting, which we are just, let's say, conditioning our algorithms to one single source of information without, let's say, taking a real advantage on this. So this is the reason why we also include Sentinel-1 data, or generally speaking, SAR data, in our classification pipelines, because we are sure that we can take advantage from, let's say, the not so well correlated information, and thus we are sure that we are adding new information and new data that can be exploited by the algorithms to detect differences. This is one reason. Another reason is that, and I know you already talked about this, is that passive satellite data, such as the Sentinel-2 data, might have problems with clouds. So might have problems with different atmospheric conditions, whereas SAR data are usually not affected. I have to be honest, I would not advise to use SAR data acquired during, let's say, heavy storms or heavy, let's say, meteorological events, because even if they are, let's say, all-weather data, it is not really true that they are not affected by heavy storms and so on. But I'm not going to talk about this. But normally speaking, SAR data can are a reliable source of information, and is a source of information that we are relatively sure that is always available. We can't say the same with Sentinel-2 data, and this is the reason why Copernicus Land Service and so on developed some mosaics services in order to, let's say, exploit the abundance of Sentinel-2 data to have global mosaics of data, so to guarantee the presence of data of Sentinel-2 data even by merging the information of time series, time stacks of satellite data. So this is just to tell you why it is important to consider also SAR data in a classification. It is not mandatory, because I mean, but it is important from a general point of view to consider in a classification algorithm all the information that really is adding new information and not only, let's say, a repetition of what is already present. The SAR data were pre-processed with a classic pre-processing pipelines. We exploited the SNAP is a software in order to pre-process the data. Of course, we do not do this by manual computation, but we exploited the Python application program interface of the SNAP softwares in order to create, let's say, an automatic pipeline in order to do this. So we started with the ellipsoid correction, so the ingestion of the right ellipsoid, the right, let's say, geometric information on the roots of the satellite. We then calculated the backscattering, so we calibrated the SAR information. We extracted the subset that is coherent with the area of interest that, if you remember, we agreed to produce land cover maps according to the Sentinel-2 tiling system. So according to the Sentinel-2 grid of data. So we were also forced to, let's say, extract from the SAR data only the portion of the related to the interest of the area of interest. We then applied a speckle filter in order to, let's say, improve the overall information in order to be sure that only, let's say, the meaningful information is ingested by the training and classification algorithms and not, let's say, information affected by too much noise. And then when we created the SAR mosaic, and we created finally the stack with the Sentinel-2 data. So this is the pre-processing of the optical and SAR data. The final aim of this pre-processing is the creation of a temporal stack. So actually, this is a data cube. So the creation of a data cube in which we have the information from the Sentinel-2 global mosaics and SAR data. Particularly, we extracted, in order to be sure to have information not affected by clouds for Sentinel-2 data, we extracted 4 Sentinel-2 mosaics data, so 1 for each quarter. And if you remember, this is also the reason why we produced the geoanalytics at a quarter level. And we also selected 4 SAR data, so 1 SAR data for each quarter. So and then we have whole the data cube composed by each of the Sentinel-2 band for each of the temporal acquisition, plus the vegetation indexes, plus the backscattering information of the SAR data. So it is, let's say, for each area of interest, you can imagine that we, let's say, created a quite big data set for the classification. Why we did this? Because we then, let's say, our, let's say, aim was to create a data set in which we were not only able to exploit the spatial distributed information, but we were also interested in the exploitation of the, let's say, the temporal behavior of the information for classification purposes. Why this? Because as I told before, now we have the possibility to have access to not just single data for one specific moment, but we are in the very, let's say, lucky position to have access to multi-temporal data. What does this mean? This means that we have the possibility to classify, so to extract information on our area of interest, not only exploiting the single radiometry, so the single information on the area on one specific time, but we have also not just exploiting the spectral signature of the data, but by creating a classification that is based upon a multi-temporal stack of data, we are also enabling the possibility to classify data, also exploiting the temporal signature of the radiometry of the data. Just to be, let's say, to clarify this point, when I talked about spectral signature, you have to imagine that the spectral signature, you can have a different spectral signature for each pixel of our area of interest. But you can, let's say, you can improve this concept by, let's say, adding the temporal dimension in the classification process. And so you will have the possibility to have for each single pixel, not just one single spectral signature, but you will have a family of spectral signatures that will characterize that area. And this is, again, all information that can be exploited by classification algorithms. Again, someone might ask, okay, but you told before that this information, you should ingest information that is not correlated. And of course, the creation of a multi-temporal stack might have as a side effect the introduction of correlated information. But take in mind, you have to consider that in this case, even if you have correlated information, let's say if you have urban areas that is stable, I mean, you are not expecting in, let's say, in an historic city center to have variation in the land use. This correlation, so the stability of the data, is an information that the algorithm exploits to produce a more accurate results, for example, on urban areas. Talking about the vegetation, if you ingest, let's say, a multi-temporal stack of Sentinel-2 data and SAR data, you will train the algorithms not only with the information related to the spectral signature of the vegetation. So, as I told before, the vegetation has a reflectance peak in the near infrared, has a different behavior in the shortwave infrared depending on the healthiness of the water content, has absorption in the red and blue, and a small reflectance in green. So we have this information, we always have this information with a single time data. But by introducing a time stack of data, we have not only this information, but the classification algorithms has also the temporal evolution of this information. And this, in a certain sense, this means that the algorithm is also able to detect the phenology of the vegetation species that we are mapping. And this again means more accurate results. So this is the reason why we suggest let's say we are used to implement our algorithms by exploiting a multi-temporal stack of data. And this is why also according to the recent scientific literature, it is the suggested way to take the maximum advantage and to exploit what it's not just the spectral signature, but also the temporal signature of the data. So this is very, very, very important concept. So reprocessing, it's not finished yet. As I told before, this is a very, very time-consuming task, and is a task that should be carefully designed according to our needs. So, for example, if we need to map a vegetated area, it would be highly advisable that we have, let's say, a temporal stack of data. If our interest is just on urban areas or water bodies, and for classification purposes, maybe a temporal stack is again also a good option, but it depends from the resources available and not, but maybe also classification on single data might be a good option. But in every classification step, I would add in every supervised classification step, there is always the need to collect training data. Why we need training data? We need training data in order to train the algorithms to recognize what we are looking for. The differences between unsupervised algorithms and supervised algorithms is that unsupervised algorithms, such as the clusterization, k-means, ISO data, they do not need training data because they are just based upon the statistics behavior of the data. But they have a huge disadvantage that they are not able to deliver labeled information. So by exploiting an unsupervised classification algorithms, we then will need to spend a lot of time to understand if the clusters are compliant with our needs or not. So this is the reason why in this project we needed the implementation of a supervised algorithm. In supervised algorithms, there is always the need to collect training data. What is training data? Training data actually is composed by geometric features, is composed by informations labeled. So information that is related to a specific land use or land cover class that we use to train the algorithms. This information can be extracted from different sources. Usually, the common practice is to extract the information from higher resolution data. Why this? Because we should be sure about the fact that we are, let's say, labeling the right training data, because this is a very sensitive step of the classification algorithms and might affect the final outcome. There might be other strategy. This depends on, let's say, the possibilities and the amount of time. For example, we can also, another strategy that might be useful for the collection of a high amount of training data is, for example, a pre-processing of the multi-temporal stack of data. For example, we could pre-process, we could clusterize with an unsupervised algorithm the multi-temporal stack, and then we can manually select the segments, the geo objects, for example, that are related to the class that we are looking for. As I told before, the collection of training data, you can try to automatize it. Actually, there are some very recent scientific works that are trying to, let's say, exploit some deep learning capabilities and ontologies in name labeling and satellite data to, let's say, trying to create an automatic train data generators, but let's say this is something that is still in the early stage of development. And I have to be honest, if you need a supervised classification, you at least now, and I think also from in the near future, you cannot avoid an expert operator that should work on the data to select and label the data correctly. This is something that cannot be avoided, at least now, unless you already have access to a good training data set. Probably, I don't know, you can find them on websites, it's or other projects websites. But again, you can use those data sets in the specific areas in which they were produced. So the training, the collection of training data is really a time-consuming task. So we have talked about the preprocessing of optical data and SER data. We have explained why it is, let's say, a good option, a good choice to create a data cube enclosing a multi-temporal stack with optical and SER data. We also talked about the possibility, let's see, what are, let's say, the improvements that we expect by doing this, with the possibility to get insights from our data, not only from a spatial and radiometric point of view, but also from a temporal point of view. So doing this, we are going to take advantage from spectral signature, temporal signatures of spectral signatures, and so on and so forth. We also talked about the ground truth collections and why ground truth collection is a very time-consuming task and a very sensitive part of let's say, the production of a land cover map exploiting machine learning algorithms. And now we're ready to talk about the classification algorithm. So in this specific project, we used the light gradient boosting model algorithm. When talking about classification, again, the classification is a branch of the machine learning theory. Of course, this is not the only feasible algorithms. There are other algorithms that can be applied on the same temporal stacks. There are certain kind of algorithms that needs the, let's say, formatting of the training data in some specific way, like, for example, the convolutional neural networks that need patches of data and not data provided in a vectorial format. But let's say in this demonstration, we exploited the light gradient boosting model for the following reasons. First of all, it is a random forest-like algorithm. Everyone that has some experience in this sector knows that a random forest is a very, let's say, good option to do classification, because it has a tree-based learning algorithms that is able to select only the information that is really useful and also deliver the information that and the informative layer that are mostly useful. Above all, it is an algorithm that it is not too much memory expensive, so you do not need a very, say, high performant hardware configuration to do this. It is an algorithm that is quite robust against the overfitting. So it is an algorithm that is designed to, let's say, deal with also redundant information. Again, even if we exploit algorithms that are designed to deal with redundant information, we should not, unless there is a specific reason, like for example, the provision of temporal signature in our stack of data, provide redundant information. This is not useful, and this is, let's say, just an exercise to demonstrate that you are able to ingest more data, but it's totally useless if there is no specific need to do this. It is an algorithm that is characterized by faster training speed, high efficiency. Of course, the libraries are already optimized to be run in parallel and distributed environments, and also take advantage of GPU, so graphic processing unit learning, and is able to handle a wide range, so large-scale data. Has every classification algorithm, let's say the classification is just one of the possibilities offered by the same algorithms. So you have to consider that the same algorithm can be used to carry out heuristic regression application. So application on regression that are not able to perform with I don't know, the ordinary least square algorithms or some, let's say, the parametric statistic method. So when the parametric statistic, let's say, is no more able to effectively represent the information contained in our data, it's a good option, the exploitation of heuristic regression application like the one featured by classification algorithms. This algorithm is able to carry out multi-class classification. Of course, it can be used to do also binary classification. There is no so much difference. It can be used also for cross-entropy applications, so for the prediction of differences in the distribution of information, and also in a ranking application. What is a ranking application? A ranking application is, simply speaking, an application that you can see every time that you use I don't know, a web browser like Google or Bing. When you type something, you have some results. These results are provided according to our rank. So these algorithms can be used to rank the information and to give you the most probable information correlated to your choice. This is just to mention some of the application of these algorithms. And we have the ground truth, the optical data, the classification. We can train the algorithms, and the training process is the process that, let's say, teach to the algorithm how to classify the information. So the algorithm actually learn how to extract the information according to our needs. Our needs are expressed by the ground truth collection. And that's the final output. So the output that we already shown before, and the output that we exploited also for the calculation of the geoanalytics. So this is, let's say, a very, I have to say, so in this training, we started to talk about the radiometric quantities at the energy. So when you see this land cover map, you have to consider that this is the results of the energy that has been recorded by the satellite, has been then pre-processed by the satellite itself, has been then pre-processed by a ground station, and pre-processed again, but by other algorithms such as the level 1 and level 2 algorithms, and then has been again pre-processed by us to create the multi-temporal stack of information, and then has been classified thanks to the collection of the training data. So a land cover map has behind all these processing steps, and this is the reason why I think these are, let's say, is a very land cover is a very good example to show what are, let's say, a very complex, what is the complexity in the exploitation of satellite data, but what is also the information and the useful information that we can extract by all this complexity and processing pipelines. So this again is the land cover map of Chanjur district. And finally, there is also the validation, the validation activities that are still in progress. But the validation activity, again, they require the collection of data, lablet data that should be exploited for the computation of numeric metrics that are able to tell us what is the accuracy of our classified data. So that's all from this session related to classification. And if there are any questions, I do hope there are questions, I will be very happy to answer them.
Kepada Bapak dan Ibu, apakah ada pertanyaan terkait dengan presentasi dari Dr. Antonio Novelli? Mungkin kalau ada pertanyaan bisa disampaikan dalam bahasa Indonesia, tidak apa-apa, nanti kita coba terjemahkan dalam bahasa Inggris. Dari teman-teman pertanian mungkin ada yang hadir di sini.
I'm sorry, I can't hear.
Antonio, I think we're still waiting for somebody, or
Okay, sorry.
Is there any question? But if there is no question, maybe we can have a break, or you have any conclusion to say to the audience?
Yes, we can let's say conclude that after what we have shown in this training is just, let's say, a demonstration of a very small portion of the possibilities that we can deliver with Earth observation data. To be honest, to exploit the real potential of Earth observation data, we should not rely on just Earth observation data, but we should also exploit the possibility to include Earth observation data in processing pipelines that take advantage of other sources of information. This because I'm talking about open source information. Open source information has, let's say, can feature a limited spatial extent. It has, let's say, as I told before, the possibility to tell you what that something is happening and tell you where something is happening, but without further information might be phenological model, a classification, or maybe the knowledge about a specific crop behind over a selected area. We can deliver, let's say, a huge amount of high-level information. We can deliver anomaly detection. We can deliver also systems that can warn you when, let's say, there is something that should not happen. There is some crops that is not featuring what it should, let's say, feature. There are some crops that might be affected by pests, or there are some crops that maybe are not affected by pests but are showing a decrease in their biomass just because there is something that prevent the irrigation. So you can really, but you know that you can't know this if you, let's say, if you do not know other information. So if you are able to put together all the information, as I shown before for the temporal signature of the data, here it is the same concept. If you have other information that can be added, a real informative content and not just a replication of the information that is totally useless, you can really achieve something useful and something that can deliver benefits to the community, to the stakeholder, can have also an economic and financial value. It can be also used to optimize the intervention, and also to optimize the financial resources, for example, to carry out more in-depth studies. As I told before, this data can tell you something is happening and where it's happening. If you need more information, you know where to spend your financial resources in an optimized way, because you know that you have a specific problem only over specific areas and not in, let's say, in a not well-defined areas. So this is the correct exploitation of this kind of data. This kind of data should be, let's say, a source of information, not the only source of information, but a source of information that should and have to be exploited to deliver optimization, decision support systems, and to make, let's say, to improve the existing practices, if these practices are not considering the possibility offered by this data. So this is, in my opinion, the real, the most important consideration that should be done in this training. So to consider the possibilities, the huge amount of possibilities in the optimization of our practices and in the management of our territories. Considering that optimization also needs a better exploitation of our financial resources, and this means if we are able to better exploit our financial resources, we might have the more resources to do more. So it's, let's say, something that is able to create a very positive trend if well applied. That's all.
Yeah, I think we have one question and from Ibu Yesi Arvelina. You may see at the chat box, Antonio. So the question is, thank you for the presentation. How about the classification rate of your applied methods and the comparative study result with the field data?
Yeah, as I told before, this specific part is still in progress. we didn't yet finalize the validation of our method. Of course, what we can show you in this stage is that there is a good visual, let's say, agreement between, let's say, what can be seen by our eyes and what is the classified areas. You can see here, these are, let's say, areas that are interested by anthropic. These are areas interested by cultivations. Also here, we can see the same, that there is a generally good agreement between the areas and the classified areas. Of course, this is a very important question, because the assessment of the results of the algorithms is important in order to understand if the whole pipeline is a pipeline worth of implementation. But again, this is still in progress, because we are still organizing the ground truth data. And as I told before, the ground truth data, it's something that should be made, is a very time-consuming task, and we are going to finalize this. But we are going to, first of all, to be sure that the ground truth data are real, high quality ground truth data, and not mixed ground truth data that can deliver problems with the assessment. I don't know if I was able to answer this question.
Ibu Yesi, do you think the Antonio explanation already answered your question? Yes, I think your explanation already answered Ibu Yesi question, Antonio.
Okay.
Yeah, so thank you. Bapak Ibu sekalian, apakah masih ada pertanyaan untuk Dr. Antonio? Oke, baik. Kalau begitu, so Antonio, thank you for your explanation, and everything. Your presentation is very interesting. So maybe after knowledge sharing session from the Indonesian expert, we have a discussion session, and you can join us again for maybe there is a question or discussion among the participants. So thank you very much. Terima kasih. We will have a break for 10 minutes, and we will come back on at 16:17. Okay.
Thank you very much, Nancy.
Thank you so much. Baik, Bapak dan Ibu sekalian, kita akan rehat sejenak selama 10 menit. Kita akan kembali lagi pada pukul 16:17 untuk melanjutkan sesi knowledge sharing. Nanti akan dimoderasi oleh Bapak Dr. Firman Hadi. Terima kasih.
Assalamualaikum Bu Sasa.
Waalaikumsalam Pak Firman.
Kedengeran ya?
Ya. Saya duluan yang presentasi.
masih sempat tuh saya diajar dulu.
Baiklah Bapak dan Ibu rekan-rekan sekalian, semoga masih tetap semangat ya mengikuti acara hari ini. Tadi setelah kita mendapatkan ilmu-ilmu yang menarik dari Dr. Antonio Novelli dari Planatek mengenai pemanfaatan data-data pengiraan jauh untuk sektor pertanian, kini saat ini kita mendengarkan sharing session dari para pakar di Indonesia yang tentunya tidak kalah menarik. Dan sudah bergabung saat ini dengan kita Ibu Dr. Insinyur Rizatul Sofiati MSc, selamat sore Ibu, peneliti dari Balai Besar Sumber Daya Lahan Pertanian Kementerian Pertanian. Kemudian ada Bapak Dr. Insinyur Dede Dirgahayu Domiri MSI, peneliti Pusat Riset Pemanfaatan Pengiraan Jauh, Organisasi Riset Penerbangan dan Antariksa Lapan, Badan Riset dan Inovasi Nasional atau BRIN. Dan sesi ini kita juga akan bisa berdiskusi secara bersama-sama dan tentunya masih seperti kemarin acara hari ini akan dipandu oleh Bapak Dr. Firman Hadi. Kepada Dr. Firman Hadi kami persilahkan.
Ya. Assalamualaikum warahmatullahi wabarakatuh. Selamat sore. Terima kasih atas kesempatan yang telah diberikan. Mudah-mudahan Bapak Ibu yang mengikuti dari hari pertama sampai hari ini ya, hari keempat, tidak bosan melihat saya. Kalau saya tidak sudah bosan ya melihat layar. Oke, kali ini kita akan berdiskusi tentang sesuatu yang sangat penting ya. Bukan berarti topik-topik sebelumnya tidak penting, karena yang sekarang ini berurusan dengan perut ya. Kalau orang Indonesia urusan perut itu urusan hidup dan mati. Jadi kita sangat beruntung ya akan menyimak paparan dari dua ahli terkait dengan bagaimana menggunakan data remote sensing untuk pertanian. Yang pertama, pembicara yang pertama adalah Dr. Dede Dirgahayu Domiri dari Lapan, tadi sudah disampaikan oleh Ibu Nancy. Beliau bagi sebagian orang kalau ketemu dengan saya begitu ya, itu Pak Dede kakaknya Pak Firman ya. Ya memang kami memiliki kemiripan sedikit dan saya menganggap beliau sebagai guru saya ya. Sejak tahun 2009 pertama kali berinteraksi melakukan survei padi ya di Gorontalo, saat itu musim bulan Ramadan ya. Luar biasa ya. Jadi malu kalau saya waktu itu tidak puasa juga, padahal sudah kepanasan saat itu. Gorontalo bulan Ramadan luar biasa. Dan beliau sampai sekarang pun masih meneliti tentang padi ya, terutama kaitannya bagaimana menggunakan remote sensing untuk memperkirakan banyak hal untuk padi ya, dengan penggunaan Google Earth Engine dan sebagainya. Dan Pak Dede Dirgahayu juga kebetulan, walaupun di dunia ini tidak ada yang kebetulan ya, bekerja sama dengan erat dengan Ibu Sasa ya. Kami biasa menyebut Dr. Rizatul Sofiati ini dengan Ibu Sasa supaya lebih dekat. Dan saya dan Ibu Sasa teman sependeritaan Bu ya dulu. Sekarang Ibu Sasa sudah senang, saya masih menderita Bu. Bu Sasa ini banyak ya pengalamannya. Salah satunya menulis buku juga ya, diterbitkan oleh IEEE atau Springerling Bu ya. Jadi buku hasil menimba ilmu di AIT. Jadi Bu Sasa juga mengenal baik Dr. Lal, Dr. Manzul dari Asian Institute of Technology. Oke, saya hentikan saja obrolan saya ini. Mari kita langsung persilahkan Pak Dr. Dede Dirgahayu Domiri untuk menyampaikan materinya. Mohon maaf karena waktunya terbatas, waktunya 20 menit, Pak Dede.
Ingatkan saja Pak.
Ya.
Kemarin tuh 2 jam. Ini ada terjemah langsung, jadi I prefer stop in bahasa ya. No problem. Slide in English. Oke, tidak ada waktu lagi, baik saya mulai. Jadi saya dihubungi oleh panitia untuk mencapaikan acara pada hari ini ya, dengan topik ininya adalah knowledge sharing and capacity building. Berarti memang ini sifatnya interaktif. Tapi di judul fokusnya pada bagaimana observasi dari permukaan bumi, terutama untuk tanaman dan water. Nah, saya difokuskan from model to operational. Jadi dari model spasial yang dibuat dari data penginderaan jauh, data satelit, bagaimana caranya bisa operasional? Karena model itu adalah pendekatan dari proses yang ada di alam. Karena memang proses di alam itu sebenarnya.
Selamat sore Pak Dede, mohon maaf.
Oh ya?
Untuk suaranya agak dinaikkan sedikit Pak, volumenya Pak. Suaranya terdengar dengan jauh Pak.
Oh, tapi nggak ada tombol puternya nih. Gimana sekarang?
Ya, mic-nya lebih dekat Pak. Oke, baik.
Sekarang
Ya, sudah jelas Pak.
sudah jelas. Oke.
Terima kasih Pak.
Tidak, background-nya sebenarnya ya dalam kondisi sekarang ya kita pasti harus ditanamkan dalam imagine kita untuk menyelamatkan dunia kita. Jangan sampai bumi yang kita huni ini keseimbangannya terganggu, terjadi kerusakan dari resources kita. Jadi kita sebagai manusia yang diamanahkan oleh Allah yang Maha Kuasa untuk di muka bumi ini ya harus bisa mengaturnya untuk kehidupan manusia itu juga, nggak hanya untuk sekarang tapi untuk kemudian. Nah, satu alat untuk bisa bagaimana kita bisa memantau dunia kita ini yang mungkin tiap-tiap negara berbeda-beda ininya luasnya ya. Berarti harus kita menggunakan suatu tool atau alat teknologi yang berdaya guna ya. Seiring dengan perkembangan teknologi itu melalui remote sensing. Kenapa? Jadi keterbatasan dari kita sebagai manusia itu bisa dibantu oleh penginderaan jauh atau remote sensing yang bisa digunakan baik itu dalam dimensi luasnya, spasialnya, maupun dimensi waktunya ya, untuk bisa memonitor bagaimana kondisi tadi sumber daya alam kita. Nah, di sini karena objeknya adalah vegetasi ya, terutama vegetasi, objek vegetasi dan air ya, yang pada umumnya meliputi hutan, perkebunan, dan pertanian. Di mana pertanian ini adalah sebagian besar sumber dari bahan makanan pokok kita. Tapi sebenarnya antara hutan, perkebunan, dan ini juga sangat berhubungan. Jadi hasil dari usaha di hutan atau perkebunan yang bisa digunakan untuk ketersediaannya dari data hasil produksi pertanian. Terus bagaimana caranya? Ya tentunya kita harus bisa mengenali ya, mengidentifikasi daripada karakteristik pertumbuhan tanaman itu sendiri. Nah, terutama tadi yang saya sebutkan bahwa terutama di sini padi atau tanaman pangan yang lain ya, yang sebagai bahan makanan pokok manusia. Jadi dimulai ketika dia persiapan tanam, ya, mulai tanam sampai puncak hingga sampai panen. Jadi ya ujung-ujungnya adalah bagaimana kuantitas dan kualitas daripada panen itu mencapai ya optimal. Paling tidak dalam masa kisaran dari rata-rata normal hasilnya. Nah, sebelum mencapai itu tentunya juga harus fenomena yang bisa mengganggu terjadinya keberhasilan panen tadi itu. Ya. Jadi akibat daripada kekeringan, banjir maupun serangan penyakit tentunya harus dipantau juga. Suara saya nggak jelas, tolong diingatkan ya sama ini. Saya nggak sengaja udah pas mic-nya gini. Nah, tentunya untuk bisa melakukan itu ya, bagaimana kita bisa memanfaatkan data satelit yang banyak ya, yang besar ya, dari berbagai macam multi sensor, berbagai macam satelit, tentunya perlu metode gitu ya, untuk melakukannya ya. Misalnya di sini dari hasil penelitian ya, misalnya untuk vegetasi, khusus untuk vegetasi ya, digunakan turunan daripada data primer daripada data pengendalian jauh ya, umumnya misalnya surfaktan, data pengendalian jauh dari berbagai panjang gelombang, sensor panjang gelombang itu untuk yang data pasif ya, atau data optik, atau hamburan balik atau backcaster daripada data radar. Jadi bagaimana kondisi daripada tanaman itu bisa diwakili oleh dengan suatu indeks namanya indeks vegetasi, yang dimana di sini digunakan data satelit optik yang memiliki kanal merah dan inframerah dekat dan biru. Jadi indeks vegetasi FVI ini adalah sebagai pengembangan daripada NDVI yang tidak sensitif terhadap kejenuhan atau saturasi pada kerapatan tanamannya, dan juga pengaruh dari base-nya dari lahannya. Tentunya dalam pelaksanaannya harus operasional ya. Jadi nggak bisa sesaat, misalnya kita melakukan penelitian selesai sesaat terus jadi paper, sudah nggak hasilnya tidak bisa tidak bermanfaat bagi masyarakat. Tentunya harus diterapkan ya, diaplikasikan sehingga bisa bermanfaat bagi masyarakat ya. Sehingga diperlukannya data yang sustain ya, yang berkelanjutan ya, baik datanya tersebut, baik dari data yang resolusi rendah terutama untuk faktor-faktor lingkungan maupun yang menengah gitu, untuk di objeknya. Seperti di sini ada data yang tadi dari resolusi rendah bisa data Sentinel-3 ya, atau Modis atau NOAA ya. Sedangkan yang menengah sekarang Landsat 8, dan yang paling sekarang banyak digunakan ya, terima kasih nih untuk pihak ESA ya, dari konsorsium Eropa yang bisa menyediakan data Sentinel-1 dan Sentinel-2 ya secara kontinu gitu, setiap 5 hari ya, atau 12 hari untuk yang radarnya. Dan kalau jika konstelasi bisa dalam hari itu kita bisa banyak menghasilkan data di lokasi kita. Dan ada juga sekarang tuh dari resolusi tinggi sekitar 4,4 meter itu dari data planet ya, yang bisa kita akses secara free, data bulanan ya. Ini sangat bermanfaat. Oke, lanjut. Nah, ini contoh bagaimana dari data Sentinel-1 kita bisa buat tadi adanya gabungan dari Sentinel 1A dan 1B ya. Itu kan berbeda ininya, berbeda pengambilannya, perekamannya, sehingga kita bisa buat komposit dalam temporal waktu menjadi 10 harian. Seperti ini bisa dilihat sini, bisa diklik. Saya buat aplikasi sederhana, jadi sampai hari ini ada berapa data gitu yang ada. Ini bisa diklik aplikasinya, hanya bisa melihat di setiap lokasi kita. Ini tadi metode ya. Ini tapi maaf nih, ini masih bahasa Indonesia, tapi pada intinya adalah bagaimana tadi model itu dibuat untuk melihat fenologi daripada pertumbuhan tanaman, baik itu tanaman pangan ya, tanaman semusim ya, maupun yang semi semusim ya. Jadi seperti tanaman tebu itu dia misalnya tahunan gitu. Kalau yang tanaman yang serealia atau seperti padi dan palawija ya rata-rata sampai 4 bulan. Ada juga yang lokal sampai 6 bulan. Jadi jika sudah ketemu modelnya, baru kita bisa menghasilkan secara spasial dari data satelit sebagai input yang tadi sesuai dengan periode waktu yang kita perlukan. Misalnya tadi pada 10 harian atau dekad dasarian. Nah ini kita coba bagaimana tadi topiknya dari model proporsional. Ini ilustrasi bagaimana. Jadi tadi kalau fokusnya vegetasi dan air sebenarnya ya ini saling berhubungan. Jadi mungkin vegetation together with water ya. Jadi ada siklus air ya yang dapat kita pelajari ya secara dinamis. Ya. Jadi pendekatan dinamik ini kita jadi bisa mengetahui proses yang terjadi gitu ya. Jadi nggak black box ya. Apa ini istilahnya kalau begini? Bukan istilahnya apa ya? White box bukan juga ya. Pokoknya kita bisa prosesnya dari mulai air turunnya. Jadi air hujan misalnya turun dari langit ya, berdasarkan proses kondensasi, rainfall atau presipitasi. Jika di lahannya itu kelerengannya kondisinya misalnya ada kelerengannya, tentunya berpengaruh terhadap air hujan yang turun. Tapi juga dipengaruhi oleh adanya kerapatan tajuknya, tajuk tanaman. Nah ini diwakili oleh indeks luas daun atau leaf area index. Nah itu ada air yang mengalir bukan ke dalam tanah yang bisa dimanfaatkan oleh tanaman, akar tanaman, tapi menjadi runoff atau limpasan permukaan. Jadi di sini sebenarnya model dinamis ini ada beberapa submodel. Yang pertama yang utama adalah model neraca air, water balance. Jadi dari neraca air ini kita bisa tahu jadi dari air curah hujan yang turun ya atau gross rainfall ya dengan pengaruh kondisi lahannya ya dan tanamannya itu menjadi hujan neto ya, yang bisa dimanfaatkan oleh tanaman. Tapi juga terjadi yang outputnya yaitu evapotranspirasi. Seperti itu. Jadi kalau tanahnya kualitas lahannya bagus, tentunya air hujan ini bisa dimanfaatkan oleh akar tanaman ya, untuk melakukan proses fotosintesa ataupun penyerapan dari hara di tanah ya, unsur hara yang diperlukan untuk pertumbuhan tanaman. Jadi tidak terjadi istilahnya banyak bocor gitu, bisa terjadi drainase misalnya atau perkolasi yang terus ke bawah yang tidak bisa dimanfaatkan atau diserap lagi oleh akar tanaman. Jadi ini keseimbangan gitu. Nah ini jadi fenomena alam ini bisa kita dekati dengan model, ya, terutama ini model dinamis. Ada juga sih model yang statis ya. Jadi kalau model statis, jadi ada istilahnya neraca air itu yang dicetuskan oleh Thornwright and Matter tahun 1958. Itu secara sederhana dalam bentuk tabel-tabel yang bisa diolah, baik itu dia data harian ya, 5 harian, 10 harian ya, ataupun dasarian atau 10 harian atau bulanan, sehingga bisa melihat di rata-rata beberapa tahun bisa melihat terjadinya endemik di suatu daerah, terjadi defisit kekurangan air atau terjadi surplus atau terjadi sebagai potensi banjir. Nah itu yang tadi ilustrasi di alam itu bisa dibuat suatu diagram namanya diagram Forrester ya, yang bisa menunjukkan proses tersebut. Jadi di sini ada tanda kayak awan itu tuh rosot, jadi istilahnya dia keluar, jadi tidak bisa dimanfaatkan oleh tanaman. Ya. Jadi artinya ada aliran airnya ya, ada aliran bagaimana proses atau informasi. Gitu. di mana parameter inputnya, parameter input tanaman, parameter input dari lahannya itu bisa diturunkan menggunakan data pengintian jauh tadi. Nah, sekarang kan tadi saya sebutkan itu sini tersedianya yang free, ya. Bisa melalui PUSFATJA LAPAN, ya, ataupun dari USGS, ya, yang data terkoreksi. Tapi kalau misalnya mau yang cepat, ya, yang near real time, ya, kalau memang dibutuhkan waktu misalnya untuk bencana, ya mungkin harus berhubungan dengan pustek data gitu. Tapi kalau yang sudah misalnya sudah tersedia yang sudah tersedia sudah terkoreksi, kira-kira ada delay sampai 4 hari atau seminggu. Ini jadi parameter input tanaman lahan itu kita bisa turunkan dari data penilaian seperti misalnya leaf area index tadi, karena akan berpengaruh terhadap terjadinya runoff. Dan juga lereng bisa diturunkan, slope atau lereng bisa diturunkan dari dam. Yang sekarang yang udah ada versi 4, ya, 30 meternya ada hole atau lubang-lubang di beberapa dataran, ya, itu udah terisi. Jadi bisa dimanfaatkan untuk membuat lereng atau aspek, ya, orientasi daripada lereng tersebut juga bisa sangat bermanfaat untuk misalnya untuk aplikasi bencana, misalnya untuk longsor dan sebagainya. Seperti ini. Nah, ini contohnya input yang lain dari curah hujan juga bisa bisa diperoleh dari data penilaian jauh. Ini contohnya yang sustain data chips, ya, dari 4,5 kilo di downscale, ya, dengan di resampling jadi agak lebih batasnya lebih halus supaya disamakan misalnya menjadi 250 meter. Ada juga Himawari 8, ya, lebih spasialnya lebih ini, cuman beberapa untuk di beberapa area belum dikalibrasi dengan data observasi di lapangan dari BMKG. Nah, ini contoh lebih detail, ya, dari tadi input tadi, misalnya soil moisture bisa diturunkan dari data penilaian jauh. Jadi dari model seperti ini, ya, bagaimana dari model menjadi operasional untuk monitoring daripada tadi dinamika dari perubahan soil moisture, ya, karena kelembapan tanah inilah yang akan menjaga kesediaan air bagi tanaman untuk tumbuh dengan normal. Ini menggunakan 2 parameter, land surface temperature dan vegetasi. FEI ini sebenarnya dalam teknik pemrosesannya ada 2 kriteria. Ini kami sudah membuat RCD-nya. Kalau minimal menggunakan indeks FEI ini karena sudah mengadopsi dari NDVI, SAFI, ARVI dan sebagainya. Kalau ada yang lebih aplikasi yang lebih khusus bisa dikembangkan dari setelah FEI ini. Nah, ini secara bagaimana menurunkan beberapa parameter tadi, ya, seperti suhu udara, karena suhu udara berhubungan juga dengan kondisi di penutupan vegetasinya dan surface temperature. Juga dengan kondisi di udara di antara tanah dan biasanya di setinggi 1,2 meter, ya, untuk ini. Jadi kita bisa mengestimasi suhu udara dari suhu permukaan dari data satelit. Demikian juga kelembapan udara. Tadi soil moisture, kelengasan lahan bisa juga dideteksi. Terus ini evapotranspirasi. Jadi ada juga secara global yang disediakan oleh Modis 500 meter, tapi kita kan untuk manajemen yang lebih detail, ya, yang lebih artinya lebih tadi disebutkan lebih presisi gitu, precision farming, kita perlu spasi yang lebih detail. Makanya dikembangkan untuk estimasi daripada evapotranspirasi ini, potensial ini dengan data satelit, ya. Tapi itu tadi yang continue, misalnya data Sentinel-2 ataupun nanti dari radarnya sendiri. Tentunya perlu penelitian lebih mendalam sampai sejauh mana sih data radar yang bisa relatif bebas, bisa menembus awan untuk bisa mendeteksi evapotranspirasi. Karena ada hubungan antara tanaman dengan tadi diagram forester kan, evapotranspirasi itu bisa dipecah menjadi 2. Ada evaporasi, ada transpirasi. Jadi Itu mekanisme secara dinamisnya seperti itu. Jadi kita paham, oh ternyata itu di alam itu memang terjadi interaksi antara berbagai yang kompleks dari berbagai parameter.
Mohon maaf Pak, 2 menit lagi.
Jadi kalau tadi diagram forase tujuannya adalah untuk berapa sih air irigasi yang harus diberikan dalam tiap periode tanaman gitu. Karena misalnya di tiap tanaman tuh memiliki koefisien tanamannya tiap 10 hari ada referensinya yang tadi bisa diturunkan dari data satelit ya. Kalau ini gimana kalau irigasi yang masuk? Ya, ini diharapkan kalau irigasi yang masuk ya jangan sampai outputnya akan lebih besar daripada input yang digunakan untuk tanaman. Nah, ini yang tadi saya sebutkan dari koefisien tanaman, koefisien crop bisa didekati oleh model umur. Di sini pakai data optik maupun pakai data radar. Jadi dari model bagaimana menjadi spasial, contohnya seperti ini. Jadi kita bisa. Jadi ini walaupun misalnya data temporalnya 10 harian atau 15 harian, tapi yang kita perlukan spasialnya adalah umur tanaman padi contohnya. Karena tiap-tiap umur 10 hari ini ada koefisien tanamannya yang berterkait dengan evapotranspirasi tanaman untuk kebutuhan air irigasi. Nah, ini sekarang tentunya model yang kembangan itu ya perlu adanya kalibrasi, adanya verifikasi dan validasi. Ini contohnya misalnya dari data satelit, ini kita contoh satu area dari data satelit ada 5 yang berbeda. Nah, itu bisa kita lakukan pengecekan di lapangan supaya model yang dihasilkan tadi lebih akurat ya atau lebih dekat dengan kondisi di lapangan. Ini caranya. Jadi dari data satelit, dari titik tengahnya, terus ke lapangan dari titik ini, ya misalnya ini soil moisture. Ini kalau dalam persen 51,5% atau 45,7 mili. Nah, kita harus di lapangan misalnya kalau menggunakan data sentinel 10 meter, kita membuat imajiner kotak 9 ini, di mana di 9 kotak itu ada informasi ya, minimal ada foto di tanamannya dari atas, dari samping untuk melihat kondisi. Oh benar ini umurnya 10, umurnya 30, umurnya 50, umurnya 60 dalam fase vegetatif atau fase generatif. Jadi untuk menyatakan satu piksel ini ya paling tidak didukung di lapangan dengan data foto yang bukan hoax ya. Ada tanggalnya, ada waktunya. Oh benar, berarti ini model ini benar. Jadi untuk kekeringan contohnya, jadi kita menggabungkan 3 kekeringan karena di alam sendiri ya itu saling berinteraksi yang menentukan keragaan performan daripada tanaman, tingkat kekeringnya sampai sejauh mana. Karena kalau semakin kering tentunya tadi air irigasinya perlu dievaluasi supaya jangan terjadi kekeringan. Nah ini contoh, ini kita kerjasama dengan Bappenas sekarang yang saat ini, juga dengan bersama Pak Firman, dengan BMKG, dengan Bu Sasa sendiri ya, kita membuat pilot project di 3 daerah irigasi Rentang, ya, Meranti dan Jeragung untuk itu tadi kebutuhan air irigasi. Ya. Jadi dibuat ini bisa diklik ininya ya. Kita belum selesai tapi ini input-inputnya udah ada. Nanti tinggal mungkin dalam waktu seminggu ini kita bisa menghasilkan spasial kebutuhan air irigasi. Nanti untuk tahun depan mungkin akan lebih ini lagi distribusinya karena dipengaruhi oleh efisiensi air irigasi. Cukup Pak Firman. Gimana Pak?
Alhamdulillah Pak. Pas. Ya, terima kasih Pak Dede. Sebenarnya sih 20 menit atau 30 menit kurang Pak ya. Waktunya, kemarin 2 jam. Kemarin 2 jam. Jadi banyak ilmu ya yang dapat kita pelajari ya. Jadi beberapa kali saya mengikuti ceramahnya Pak Dede ini masih belum mampu menyerap. Jadi kalau 20 menit sepertinya akan ada banyak pertanyaan ya, karena Pak Dede menjelaskan bahwa jangan sampai penelitian itu hanya menjadi ajang untuk menulis untuk hanya di paper saja ya. Jadi harus from model to operasional ya, sehingga apa yang diteliti, apa yang dikaji itu menjadi bermanfaat. Kemudian bagaimana menggunakan remote sensing ini dalam dimensi spasial dan waktunya ini untuk mengatur bumi, mengatur produk pangan ya supaya berkelanjutan lah. Dan beliau memaparkan banyak model ya. Kalau yang dari agromet begitu katanya seharusnya sudah hatam ya, sudah paham sekali.
Wajib.
Memang modelnya harus dinamis, kompleks ya, karena kita bekerja dengan alam ya. Walaupun model itu penyederhanaan dari alam ya, dari sesuatu yang kompleks, namun diharapkan bisa menduga ya tadi bagaimana kebutuhan irigasi. Terima kasih sekali lagi Pak Dede. Kemudian berikutnya kami berikan kesempatan kepada Ibu Sasa. Nah, Ibu Sasa ini orang penting di Kementan ya, terkait dengan siskrop. Mudah-mudahan ada banyak
yang cerita nanti Bu Sasa nih, apakah yang saya lakukan benar atau tidak gitu aja.
Oh iya benar, terima kasih. Jadi from model to operasional. Nah, jadi yang berwenang dalam operasionalnya ini adalah Bu Sasa. Nah, Pak Dede memimpikan, oh ini idealnya begini. Ternyata kata Bu Sasa, wah ini Pak salah. Kembali lagi kan ke modelnya, bagaimana menyempurnakan. Mungkin begitu ya kira-kira. Jadi silahkan Bu Sasa, kita punya waktu. Kalau sampai ini kan dengan diskusi itu sampai 5.30 ya. Berhubung tadi Pak Dede ada lebih 5 menit. Jadi Bu Sasa bolehlah 5 menit juga supaya adil. Silahkan Bu Sasa.
Okay, thank you Pak Firman. Maybe I will present it in English because I saw that the participant is not only from Indonesia, right? It's also
silakan.
Yes, it's also from outside Indonesia. Okay, so I will share screen. Sudah terlihat Pak?
Udah Bu, udah kelihatan.
Ini suaranya siapa Pak Ilham ya?
Good luck Bu Sasa.
Okay, thank you Pak Ilham. Okay, I would like I will present my Indonesian experience, especially Ministry of Agriculture experience for using remote sensing for agriculture. And we also have a challenge, but it's not only for crop monitoring, but also other soil mapping and other application. Okay, my presentation is more to application, not about the methodology, the detailed methodology about the remote sensing. I will tell about Indonesian experience and challenge. Actually, in Indonesia, in Ministry of Agriculture, we have 3 periods of the remote sensing data utilization. First, in non-satellite data era, we use photogrammetry before 1970, but not intensively use photo udara, air photo is 1970 until 1981. And the second one is transition era. It's still used photo udara, air photo, aero photo, and then also use the printout of the satellite data is year 1982 until 2004. But in 1997, in the middle of that era, we also use a digital data, satellite data for paddy crop research. In that time, we have collaboration with AIT and also NASDA Japan. Because in that time, JAXA Japan is the name is still NASDA Japan, and now from 2005 until now, we intensively use digital satellite data, and in 2014 we already implemented the satellite data for implementation or operational use for Ministry of Agriculture especially. And during the research and development, we use many kind of vehicle. First, besides satellite data, we also use try to use a drone and also airborne. We collaborate with Restec Japan, and that time the activity coordinated by BPPT and also Kementerian. And we also have collaboration with Lapan. We use Lapan surveillance aircraft. In that time, we also use the aircraft for paddy mapping, and also we hope actually in that time to map the flood in that in Subang area, because if we use the satellite data, it's the time series is too rare, and we need to more frequent data. If we use more this data, it's not the spatial is not too detailed, but it's too rare, and we hope we can have the more detailed image data. And we try to use Lapan surveillance aircraft to do the mapping. But in that time, until now, we still not operation yet the research result. And for land mapping, we use many kind of satellite data. For one exploration map, we use satellite data like Landsat TM and contour map, and also in that time we use US navigation maps from Joint Operational Graphic or JOG. And in one reconnaissance map, scale in 1 to 250,000, we use Landsat TM 7 and or Landsat 7 or 8 and SRTM. And also we use Iconos like very high resolution data. And we also we already have map the detail or semi-detail soil map for whole Indonesia in scale 150,000. We use satellite data like SPOT also besides Landsat, and also very high resolution data like Iconos, QuickBird, View, and also aerial photograph. And we know that all of the consideration, all of the decision, we have to use paddy mapping. So it means that we have to make standard of paddy mapping. And since 2010, MOA mapped the paddy area using the very high resolution data. But in 2018, BPN, they update the data 7.1, but it means that MOA, it means that it's influence to the MOA decision. And then MOA try to make some collaboration with BPN, BIG, and also Lapan to update the map. And in 2019, we have 7.46 million hectare of paddy field. But we still have to update every year of paddy field. So it means that we still need the satellite data to do that, because we know that paddy map in Indonesia and also maybe in other countries in the world, we have conversion of the land to another land use. So it means that we have to map that intensively or periodically. Second one, we have to make the map of the paddy field conversion. The conversion of paddy field not only used for the infrastructure settlement industry, but also it can be used for estate crop like oil palm, coconut, and others. It means that we have to do in some area to map what kind of conversion of the paddy field. So it means in every year we have to map that paddy field map. Paddy field map also can satellite data can also identify the abandoned land. So it means that for extensification of the agriculture, we not only doing by intensive management, but also we extensification. We also try to make some extended of the paddy field, but it's very difficult. So it means if we have to make the paddy from the forest, I think it's not possible. So it means that we have to see or find the abandoned land to be converted to agriculture or the paddy field area. So from that map, so we can identify land suitability map, and also from that map we can analyze for the land potential map, and also we can recommend it like fertilizer and also another management. So this map is the area from the swamp. So it means that during the dry season, that area can be recommended or give more than can be supported. Can be supported the production of paddy when the other land cannot planted by paddy, but in this area maybe they can extend the area to be planted by paddy or other crop. It means that we can support it the production of crop during the dry season. So it means the time sharing of the satellite data, it's very useful to map which area can be planted during dry season in that wetland area. And this is the roadmap of the journey of the crop monitoring, standing crop we call. So in 1997, actually we already have research about the paddy growth phase. But in that time, it's not useful for others, but only for the researcher itself for write in the journal. And 2014, it's implemented already. So it means that during since 2014, we try to find or collect all of the model of the standing crop or paddy growth model to be implemented to fulfill our ministry in that time. Our ministry asked request. So it means 2014 we collect all the inventorize of the inventory of the data of the model from LAPAN, from PPPT, or also from IBB. And then we have to select which one can be used for operational use. In 2014, 2019, we use it for implementation already. But in that time, we only use the optical data of satellite data. We use first using MODIS SERA, and then Landsat 8, and then Sentinel-2. In 2020, because we have a problem with the cloud cover during wet season, and because in the wet season we intensively planted by paddy, so we have to know about that the production of the area of plant of paddy during that time. So we have to consider to use the SAR data. So it means that 2020 we already implemented the standing crop model of paddy using SAR data. It means that this time the available data is Sentinel-1. So we use Sentinel-1 to do that. We have collaboration with LAPAN to develop the model. And until now, we use that one. And the model or the analysis result can be provided in the information system or SysCrop. But in the next, we still have to be have challenge. We still have assignment for another crop like maize and also sugarcane. So it means that we have to do more research for another crop. So I think this already know for the remote sensing researcher. This is the pattern of the paddy. But we have to consider that if the area is the flooded, so it means that like in LAPAN they provide also flooded area or flood area of the paddy field, and also what is drought area of the paddy field. But we have to combine with the paddy fase map, because maybe the flooded area is not only because of flood, but it also maybe because of inundated or preparation, land preparation for paddy planted. And this one is the pattern of the paddy. The left side is the MODIS from the optical data, and the right side is from the SAR data. The pattern is, I think it's almost same, but the optical we use vegetation index, but for the SAR data we use backscatter data. This is from the Lapan. This one is the pattern of the backscatter, and the below one is the ratio of the HH and HP, I think, Pak Didi, ya. That's one, the ratio of the two polarization. This is more good research than if we use only the single polarization. And this is one example of our model, because the model we have to create for the three kind of the ecosystem. Three kind is first is paddy for the paddy irrigation paddy field. The second one is the rain-fed paddy field, and the third one is the wetland paddy field. So it means we around 21 of the model of the rice production. And this is the RMS error. Is around between 0.17 and 0.27. And this is the implementation of standing crop. Not only if we have just provide the standing crop or paddy fase 6 of type of paddy growth fase is not cannot be used. Maybe we just only know about that vegetation one, but we have to translate for the decision maker and also for farmer. So we have to combine with the climate model, climate map, so we can know if that the paddy in that area, if the vegetation one. So it means that if the next month it still should be have enough rainfall, but if not enough rainfall, so we have to consider for the irrigation for the local government to consent to that area, or we have to change to the another variety of paddy that can tolerate with the drought. And this one, the information is until sub-district. So it means that the local government can use it for operational. And this is the information that can be derived from that paddy field. So we can know maybe if that this month the vegetation one, so it means that that area have potential area for the next 4 months, and so on, until if we know if that's a bare land, it means that already harvested. So it means that that area is potentially to be planted for the paddy. So why we use 15 days data? Because if we can cover whole area of Indonesia, so it means we have to wait for until 15 days that can be covered for Sentinel-1 for whole area of Indonesia. So it means we consider to provide the data every 15 days. And this is our syscrop. This is our syscrop 1.0. So this only provide standing crop, 6 of standing crop for whole Indonesia, and the accuracy is 19 up to 90% for province and also for district level. And that system information system is mobile friendly category information, and data information is about productivity estimation. This is for the Sentinel-2 for SysCrop 2, and the facilities can be downloaded for a sub-district, district, and province, and also national. And this is our SysCrop 2, and it's provide. This is the information provided in those in this information system, standing crop, and also productivity. And beside that, we also provide the recommendation of the fertilizer. And the next future, we also will provide the water need, like they mentioned about that. So we also will provide those information, and we also will provide the IP. IP is index pertanaman, like how many times the area planted by padi every year. And this is the facility of that system information. We can click the map, and the information will be appear, like how many hectare of the paddy field and productivity, and also how many percent the area planted by paddy, and how many percent area we already bear, and what is already or available for the next plantation, and also how many area already prepared will be planted by paddy. And this is another application. If we know, if we analyzes the data every time series, every year in the same month, so we know which area are intensively planted by paddy. So it means that the territory can, local government can decide which one need the water every what month they to be deliver the water to the area. And this is another application of the standing crop. So if we know the vegetation, the phase of paddy, so it means that we can estimation of the fertilizer, pesticide, and also seed, and also water. So if we know the how many time the area planted for 1 year, so it means we can also plan the target of planting, and we can also estimate how many stock of paddy. So, and we can also estimate when we can harvest the paddy, and how many hectare and how many ton the production of the paddy for the national level, or also for province, and also the sub-district of district. So this one is another application. So we can also identify the drought area, and what is the use, what is the utility utilize. We can utilize this this information for this one, agricultural insurance. So it means that now the agricultural insurance already implemented for paddy and cow, and also for next maybe for chili and salad. So it means that if we know if we saw that area like that, so it means that the remote sensing is very useful, and is to support the agricultural insurance. So this one we use drone to estimate the area, which area planted by salad or chili. So it means that the officer of the crop insurance can help. It can help the officer of the crop insurance. And another one, not only using satellite data, we also produce one kit, smart soil sensing kit. It's the principle of remote sensing you use for this kit or the tool. It can be what is identify the soil chemical properties. It can be measure pH, C organic and total, P2O5 and Kalium, and also pre-dry extract and other soil chemical properties. And it also equipped with decision support fertilizer recommendation based on soil properties, like status of nutrient and how the nutrient need for rice, corn, and soybean. Maybe next we also in the next future we also can do the recommendation for horticulture and plantation crop. And this is how to use that equipment, that tool. And it's very useful for the decision maker to decide how many fertilizer are needed to this land.
Mohon
So,
maaf, Bu Sasa.
Okay, tinggal satu, one slide. Okay, this is the last slide. We face the problem, but I don't like to say it problem, but challenge for us. The challenge for the future agricultural development using remote sensing data is the continuity of the data, like Pak Didi said before, mentioned before, that the continuity of ability of satellite image data and tool is still depend on other countries. So it means then we should consider to make our own satellite data. And the model and result of remote sensing analysis is still in doubt. Before I also have a meeting with the statistic person, I also have intensive discussion with them. They still doubt about the remote sensing analysis result. So it means that we have to improve our methodology to gain the better accuracy to can satisfy for supporting statistic data. So and also some people also still thinking because to use the satellite data they have to spend expensive initial investment. So it means, but for the operational, I think that's more cheaper than use manual or the conventional method like survey for whole paddy field in Indonesia. And innovative technology using remote sensing, we can develop this, identify the potential of farmland as a food supplier and food system early warning, irrigation management using satellite data like Pak Didi said before, and development of soil condition detector integrated with agriculture machine. So it means it can be put the tool of the soil detector to the machine like tractor, tillage, planting tool, and fertilizer applicator, and also cooperation with various parties for development and for mass production for the tool and also for our model. I think that's my presentation, Pak Firman. Thank you for attention. And Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih Ibu Sasa. Dari tadi saya kesulitan ini mencegat untuk memberhentikan di mana, karena antara slide itu tidak ada proses bernafas sepertinya ya. Nafasnya panjang sekali nih Bu Sasa. Banyak sekali informasi yang kita simak ya, yang kita dapatkan dari Ibu Sasa, mulai dari bercerita sejarah ya, sejarah penggunaan remote sensing di Kementan. Kalau dulu Departemen Pertanian, mulai dari tahun 70-an, 90-an. Namun ini off the record, tapi saya sampaikan di umum ya, Bu Sasa sering curhat ke saya tentang ini di Kementan remote sensing ini sulit sekali digunakan, karena bisa jadi tadi berkaitan dengan kesimpulannya Bu Sasa bahwa menurut ahli statistik perlu ditingkatkan lagi tekniknya agar akurasinya semakin meningkat. Jadi akurasi meningkat ini sepertinya berhubungan baik ya dengan semakin diterimanya penggunaan remote sensing oleh kementerian lah. Jadi dengan adanya banyak kerjasama dengan JAXA, dengan NASDA ya dulu Jepang, kemudian dengan EIT, dan mungkin dengan radarsat juga pernah ya, dengan BPPT ya, menggunakan data radarsat di Karawang atau di Indramayu, sehingga Bu Sasa tadi menjelaskan
Dengan IPB,
sistem.
Pak.
Oh, IPB juga ya, benar, IPB dengan IPB juga yang nasionalnya ya, IPB, ITB enggak ya, enggak Bu ya?
Belum.
Belum ya, belum. Nanti mungkin dengan Makassar juga ya, dengan Hasanuddin, dengan Pak Ilham nih, atau dengan ITS, dengan Ibu Filsa kemarin bisa bekerja sama karena sekarang sistem yang berkaitan dengan padi seperti Siskrop 2 itu sudah canggih lah. Dari versi 1 ke versi 2 itu hanya hampir setahun ya, kurang dari setahun. Dari Desember ke Oktober itu hanya 10 bulan atau 9 bulan. Mudah-mudahan nanti versi 3 dalam waktu 4 bulan lagi Bu ya? Enggak. Diharapkan ada juga informasi tentang jagung dan tebu ya. Ini yang masih menjadi PR karena mungkin modelnya masih belum ketemu, tapi sudah mulai bukan hanya menerapkan tapi juga membuat teknologi tepat guna ya. Tadi ada apa namanya Smart Soil Sensing Kit yang bisa mudah-mudahan tidak dijual mahal ya. Kalau jual mahal kalau saya biasa Bu.
Belum ada yang ini Pak
Belum ada
memproduksi secara
pasarnya.
massal. Ya.
Oh iya, masih testing ya. Ya jadi dan pertanyaan besarnya adalah mungkin request ya, harapan ketergantungan dari sistemnya luar. Nah ini sudah dari puluhan tahun yang lalu banyak ahli remote sensing ingin paling tidak kerjasama lah dengan Thailand atau dengan Filipina ya, Malaysia. Jadi sangat menarik sekali kedua topik ini. Kalau boleh saya analogikan dalangnya ini ya untuk yang dikembangkan ya, man behind the gun-nya adalah Pak Dede bekerja sama dengan Kementan membantu mengembangkan Siskrop, dan bukan berarti hanya Pak Dede saja, ini banyak orang banyak yang terlibat, koordinasi antara lembaga sehingga menghasilkan satu sistem yang sangat aplikatif dan sangat bermanfaat kalau menurut saya. Jadi kami buka sesi tanya jawab dan kami undang juga rekan dari Planetek atau dari yang
Mungkin
lain.
Saya mau meluruskan satu
ya, yang tadi ya.
Yeah, jadi for the agriculture ministry, they already use it and they already intensively use for operational using remote sensing data for some, not only for crop, for paddy, but also for estate crop and other. Maybe they also our ministry is very like remote sensing data. So I mean every field he asked to use remote sensing data to monitor or the minutes to manage the agriculture. So, but it's very difficult to us to convince for the BPS. Because the accuracy of the remote sensing is not too high, so it means we have to improve the methodology of the remote sensing data to gain the accuracy. But they not, but mereka tidak tertutup kemungkinan untuk mau menggunakan itu asal remote akurasinya tinggi, Pak.
Iya, ya. Terima kasih atas koreksinya. Jadi memang di tingkat nasional memang bukan hanya Kementan ya yang berkepentingan terhadap estimasi produksi padi, bagaimana menentukan kebijakan ekspor impor. Kalau ekspor kayaknya tidak ya, impor. Kalau sekarang itu juga BPS yang pernah kami alami juga ketika menghitung lahan baku sawah, kemudian dibandingkan dengan BPS kok beda jauh ya. Nah ini yang masih menjadi challenge. Tadi ya Ibu bilang challenge, bukan masalah, tapi sebuah tantangan. Ya, jadi mungkin Dr. Manzul sebagai kakaknya Bu Sasa di Thailand, please Dr. Manzul.
Sasa, very nice to see you again.
Hello, Mansur. Nice to see you too. Nice to see you again.
Nice.
It's a long time not to see
We
you.
had a lot of collaboration. Both Hadir and Sasa were our colleagues in AIT. Yeah, they work in our center. So I'm very happy to see both of them doing very well. Okay, thank you. So for Sasa, I just noted few points. This system you are talking about, SIS crop. So you do the crop type, identify the crop type. You also identify crop irrigated area, rice area production. I think all looks good. But my question is how this system works. It's automatic mode or semi-automatic, or how it works? Because if you look at Indonesia is such a diverse and large country. So there should be some automatic process. Otherwise, it will be very, very difficult. So I just want to know about that. Question number one. And question number two, you also talk about drought, SPI and KBDI. And KBDI, I think, from Takeuchi Sensei, from the Tokyo University. So how you are implementing? You are directly using his data or you are processing locally? Yeah.
Okay, Pak Firman langsung dijawab.
Oh ya, langsung.
Okay. Thank you, Dr. Mansur. Nice to see you again. It's a long time not to see you. Okay, so the first question is, it is automatically. So we use Sentinel-1, and then the process in the GEA, Google Earth Engine, and then we downloaded the data and another automatization machine using database. We also doing by automatic one. And another question, the second one, actually we don't use it for now. So until now we still use CATAM, crop calendar information system, but in that time we use not by using remote sensing data, but it's from the ground data. Maybe maybe next we can also use it. But actually, I already have the assessment to use the data from remote sensing for agriculture insurance. But I compare the data from Takeuchi Sensei and also from the Lapan.
I see.
And and I already the paper already published in one international proceeding. Maybe I can send the link of the paper to you.
Please do that. Just a last point. You're talking about insurance. We are also working in a insurance weather insurance in a project in Tajikistan for cotton and wheat right now, and we are working with an insurance company to develop this insurance product. Maybe I'd like to know about this more, but later, not now, because I think we should give the floor to other questions. I'll contact you separately.
Okay, sure. Yeah. Okay, so we can contact to discuss about that. Yes, thank you.
Thank you very much, Dr. Manzul, for your comment and questions. Kita akan pilih dulu pertanyaan dari chat ya. Yang pertama dari Dr. Yesi. Sebenarnya ada dua pertanyaan ya. Ada satu ya, yang satu lagi untuk Pak Dede. Mungkin Pak Dede dulu ya. Pak Dede, apakah ada rencana Lapan meluncurkan satelit sendiri khusus untuk pertanian dan bencana?
Itu sebenarnya yang bisa jawab bukan saya, Pak. Kalau di sini
mungkin ada kisi-kisi begitu, Pak. Ada gosip.
Arif atau yang dari dulunya dari penerbang dari satelit itu bisa jawab kalau ada pesertanya gitu. Karena sih intinya kan semua itu dari ini Pak, dari user kan. Jadi kalau kita negara kita tuh luas, jadi kalau hanya dengan global saja tentunya banyak fenomena yang ada di lokal nggak bisa terpantau, Pak. Jadi perlu jadi itu. Apalagi untuk bencana yang tidak bisa terjangkau oleh ini. Kalau kita sebagai peneliti aplikasi, ya harusnya kita mandiri.
Iya, iya.
Mandiri ya. Jadi karena itu tadi lokal itu yang agak berbeda. Gitu. Nah, seperti kita ketahui juga, kita juga di musim juga beda-beda. Kan di sini banjir, di sana kering. Itulah tantangannya. Jadi emang perlu, harusnya sih ada, Pak. Tapi sebenarnya pernah dirintis yang dengan dengan IPB.
Jerman ya?
Ya, ini
TUPSAT masih berjalan.
Ya, ada tuh sampai berapa? 3. Makanya kalau ada yang ini bisa, ada yang bisa bantu nih yang dari Pusteksat penerbangan. Sekarang namanya saya lupa nih, nama yang kalau udah bergabung dengan BRIN itu paling itu saya jawab, Pak.
Oke,
tapi kalau tadi
kasih.
mengenai, mungkin saya tambahkan tadi yang tentang pertanyaan Pak Manzul itu. Jadi kami juga sebenarnya untuk asuransi itu kan dilihat dari resikonya. Ya, kalau itu dari permintaan PT yang menangani itu, ya kalau bisa itu informasinya itu jangan lebih kurang dari seminggu. Jadi harus sebelumnya gitu. Karena untuk mengurus proses klaim asuransi itu perlu proses gitu. Jadi kalau kita bisa memberikan informasi early warning terjadinya kerusakan dari tanaman akibat kekeringan, ya akibat banjir atau pencemaran penyakit, itu sangat bermanfaat bagi mereka. Jadi untuk mengecek klaim-klaim asuransi dengan cepat. Tidak perlu semua gitu. Dengan bantuan teknologi remote sensing ini, kita bisa membantu mereka. Jadi untuk kalau udah pasti ya udah nggak perlu. Kalau udah pasti emang itu rusak ya udah, kerusakannya sangat berat. Tapi terutama yang masih abu-abu kan, yang masih abu-abu. Ini klaimnya minta asuransi. Tapi kalau kita punya sebaran spasialnya, bisa dilakukan sampling. Oh ini emang benar bisa diterima klaim asuransinya. Jadi gitu, Mr. Manzul dari saya. Karena saya juga pernah kerjasama tentang hal itu.
Ya, terima kasih Pak Dede. Kemudian untuk Bu Sasa, apakah ada rencana ya Kementan mengembangkan pertanian di wilayah gambut atau di wilayah rawa? Masih mute, Bu?
Ya, gambut atau rawa?
Rawa.
Kita FK kita sekarang ada kegiatan namanya food estate ya. Di situ yang di Kalimantan Tengah yaitu adalah sebagian adalah rawa yang digunakan. Tapi kita harus juga melihat rawanya seperti apa dulu gitu kan. Dan sebenarnya banyak sekali kayak di Kalimantan Tengah itu kan kita punya wilayah-wilayah rawa yang ditanamin padi. Di sana ada namanya padi rawa ya, yang usianya bisa sampai 7 bulan, 8 bulan gitu. Lah itu sudah dikembangkan dan sekarang kita kembangkan misalnya dia IP-nya cuma 1 kali gitu, kita tingkatkan jadi 2 kali dan seterusnya dengan memberikan teknologi ya tentunya dengan tidak merusak ekosistemnya, tetapi kita lakukan sesuai dengan potensi atau istilahnya kearifan lokal ya di situ seperti apa kita bisa kembangkan dan dengan memasukkan teknologi yang sudah kita hasilkan. Itu Pak jawabannya.
Terima kasih Bu Sasa. Jadi yang di sini bukan hanya ekstensifikasi ya, tapi juga intensifikasi dengan kearifan lokal ya. Jadi
ya.
Ini
karena kita dalam ekstensifikasi juga kita kesulitan mencari lahan kan, kita tidak boleh membuka hutan ya. Untuk bisa menggunakan lahan-lahan hutan untuk pertanian kan kita harus melihat status hutannya seperti apa dulu gitu kan, dan itu tidak banyak. Jadi kita ngelirinya ke rawa, ke wilayah-wilayah rawa, tetapi kita harus melihat tidak dengan merusak ekosistem, tetapi yang rawa-rawa yang memang sudah potensi untuk bisa ditanamin padi. Dan yang dulunya rawa-rawa yang tidak menghasilkan sekarang sudah bisa menghasilkan padi. Nah, rawa biasanya pada saat musim panas atau musim kering itu dia malah bisa mensupport atau lebih luas dia bisa ditanam, karena kan ada yang surut ya, wilayahnya surut, tetapi dia masih berair gitu lah, dia kita gunakan untuk padi, sementara yang lain mungkin sudah kekeringan gitu kan, di wilayah lain kekurangan air, tetapi ini malah kita tanamin padi untuk bisa mensupport wilayah pada saat musim kemarau gitu.
Oke. Ya, berhubung waktunya.
Ada pertanyaan lain kayaknya Pak Anjar ya?
Iya, bisa lewat chat saja Bu. Langsung ya, supaya kita bisa berikan kesempatan kepada Antonio mungkin memberikan komentar atau masukan. Ya. Silakan jawab lewat chat Bu ya. Terima kasih. Mohon maaf Pak Anjar. Bukan karena mentang-mentang saya jadi moderator semena-mena Pak ya.
Ya, Pak.
Any question from Antonio, maybe, or comment?
Yes, I have just some comments regarding the, let's say, the expectation of remote sensing data for statisticians and or statistics offices. Have to say that this is a very wide and discussed topic nowadays, because we have this trade-off between the possibility to have very wide areas covered with timely and high frequency information, but there are concerns about the accuracy of the data and the estimation that we can deliver. But when when we heard this kind of discussion, I have to say that okay, but this is the starting point. Of course, I mean, this is not the starting point, because we already are in a good position to deliver more information, and of course we are in the position to exploit data fusion, to fuse different sources of data to deliver more accurate information. And actually this is also what is done by some Copernicus services, like the atmosphere and climate change services, for example, with the reanalysis data or other data that exploits data assimilation models. But what it is important to highlight is that it is true that we do not have maybe the accuracy that is let's say that should be delivered for a statistical office, but at least we do have information. So I mean, it is important to at least to have this, let's say, to know this, and that if we have information, we can exploit this information maybe to deliver more accurate services for insurances. We can exploit this information to have a background data for our evapotranspirations and irrigation models. Of course, it is true that if we use open source satellite data, I mean, these are data free of charge. So we cannot expect from free of charge data to deliver what we usually pay or what we are usually willing to pay. So, I mean, it is very important to consider that now we have this very big amount of information, but we should also consider that open source information now has this limit, but this is not, in my opinion, not a limit, but now has this potential application. So if the resolution is not enough for what we need, at least we have background information. So we are in the position to exploit free of charge data to improve, optimize, and also save money for our subsequent analysis. Just to make an example, for the irrigation system or for insurances and so on. So we have open source data. We might be able, we are able to deliver geoanalytics that might be exploited for insurances. Why this? Because we have very long time series of data and we have the capability to process from a statistic point of view this data. So we detect anomalies. Of course, if we detect anomaly, we can, let's say, highlight where these anomalies are higher, and we have the possibility to prioritize our checks. So in my opinion, it is true that, okay, we do not have the accuracy and the precision that maybe is the final target that open data should, let's say, reach in the near future, I do hope. But at least we have a huge amount of information that, and we are able to exploit this information to have a background of data that we can exploit to a lot of different downstream application. So this is, in my opinion, now this is a very, in my opinion, very good period to develop new models, because actually there is a very, I mean, we have this huge amount of information, and soon I'm sure that we will have also better, more resolved information. So now, I mean, we have to focus our attention to understand how to get the maximum from this data, because I'm sure that we will have better data, more dense data, and then, I mean, the challenge will be how to, let's say, extract again all the maximum from this data. So this is my opinion, but I agree that in some specific application, the exploitation of only remote sensing data, open source remote sensing data, might be not enough to fulfill some specific needs. But this is the reason why I stressed a lot the fact that at least in agriculture, there is the need to collect user requirements, to collect, let's say, to co-create together with the stakeholders, together with the agriculture community, all the requirements. And then the duty of the technical and scientific staff is to answer and to tell, okay, with open source data, we can deliver this. Maybe open source data might be not enough for this and that specific requirements. Maybe to fulfill these specific requirements, we might need different resources to buy, for example, commercial data, or to ingest other sources of data. So, but in my opinion, we should always consider that the remote sensing data is just a branch of the amount of data that we can exploit for our purposes. Of course, we should exploit open source information, but there are also other sources of open source information. And when open source is not enough, we should act in order to acquire the information that we need. Thank you.
Thank you. Oke, kalau boleh saya berkomentar ya. Saya merasakan komentar dari Antonio ini seperti gregetan begitu ya. Ada potensi, banyak data, kemudian dari sisi statistician dianggap masih belum cukup akurasinya. Padahal dengan satelit, wilayah yang luas, kemudian sering didapatkan ya datanya timely, itu yang sebelumnya tidak mungkin menggunakan survei lapangan secara statistik. Nah, di sini dapat diperkirakan angkanya berapa sih seperti itu, dan ini merupakan kita sudah ada di posisi yang baik nih, sudah banyak teknik data fusion, machine learning, dan macam-macam sebagainya untuk menghasilkan satu informasi yang lebih baik ya, bagaimana mengembangkan model yang baru, dan saat ini adalah saat yang tepat untuk bekerja sama ya. Jadi co-create, bagaimana menentukan mulai dari user requirement, apa saja sih yang dapat kita peroleh dari remote sensing, kebutuhannya apa, kemudian ada mix and match, supaya teknologi yang ada sekarang, pengetahuan yang ada sekarang, dan terutama semangat ya. Jadi saya merasa ini Antonio ini sangat gregetan, gemes gitu. Ini sudah bisa nih, tapi kok masih saja ada yang meragukan. Dan sebenarnya itu bisa dipecahkan ya dengan saling diskusi mungkin ya. Mungkin silakan komentar dari Ibu Sasa atau Pak Dede atau mungkin dari yang lain.
Boleh saya komen Pak mengenai
ya,
itu?
Silakan.
Ya sebenarnya kalau saya lihat dari sekarang sih, kemudian saya punya banyak teman-teman BPS, mereka sebenarnya tidak close ya terhadap remote sensing. Mereka sebenarnya terbuka dengan pemanfaatan remote sensing ini. Malah saya dengar tadi waktu pas di FAO, teman BPS itu presentasi akan menggunakan data remote sensing untuk sensus. Sensus tahun ke depan gitu kan. Sebenarnya challenge kita adalah akurasi, meningkatkan akurasi itu saja sebenarnya. Mereka tidak menutup kemungkinan untuk menggunakan remote sensing ini. Asal akurasinya tinggi, terus kemudian bisa dipertanggungjawabkan ya. Karena kan kita sebenarnya kan remote sensing itu banyak sekali yang kita temuin sekarang itu adalah misinterpretasi ya. Misinterpretasi misalnya padi dengan jagung dengan tebu yang ditanam di tempat yang sama di sawah-sawah juga gitu kan. Apalagi nanti kalau sudah ke lahan kering yang seperti Pak Anjar tanya tadi, kalau lahan kering kan sudah semakin ribet lagi Pak Anjar. Jadi lahan kering itu nanti akan ada banyak tanaman gitu, tidak hanya padi tapi juga rumput gajah dan lain. Malah sekarang saya dengar waktu pas saya survei di Madura itu malah di sawah irigasi sekarang juga ada rumput gajah ditanam di sana karena lebih menguntungkan gitu loh. Nah, itu yang tantangan kita adalah kan meminta mereka untuk mau menggunakan remote sensing, mereka sudah mau, tetapi akurasi yang harus kita tingkatkan itu sebenarnya. Kalau akurasi tinggi, cuman masalahnya akurasi ini ketika saya produksi ya, kita punya pengalaman, saya kebetulan studi saya tentang produktivitas, itu saya tidak bisa membandingkan dengan data BPS karena data BPS kan tidak kalau kita kan time series ya, jadi bulan per bulan kita bisa melihat produksinya berapa, tetapi kalau BPS itu kan akumulasi, jadi data yang dipublish itu kan akumulasi tiap 4 bulan sekali ya kalau nggak salah ya. Nah itu yang kita nggak bisa bandingkan gitu loh. Nah ini yang mau kita jadikan poin atau referen untuk akurasi tadi apa gitu kan? Itu yang harus sekarang kita lakukan adalah kita melakukan ujian sendiri Pak Firman. Jadi dengan bantuan dari extension officer kami atau DPTP AI IT seluruh Indonesia, the whole of Indonesia in whole province, they help us to collect the data, the productivity, the ubinan for our staff to develop the productivity model for remote sensing using remote sensing data, because we cannot have the ubinan data in individual data from BPS because it's very secret. Even though for the plat merah what is that institution, so we cannot get the data. Iya, walaupun sama-sama pemerintah karena memang ada aturannya. Makanya kita harus mencari sendiri data tersebut, tetapi data tersebut harus collect sesuai dengan metodenya BPS. Jadi kita membeli ubinan sendiri, terus kita ada bimtek yang dilakukan oleh teman-teman BPS terhadap teman-teman kita yang di lapangan, sehingga kita bisa mengkolek data tersebut sesuai dengan metode yang dilakukan seperti yang dilakukan BPS itu. Karena kita nggak bisa dapat misalnya sebenarnya kan mereka mengkolek data di KSA ya. Nah, kalau kita dapat data itu saja kan enak gitu kan. Nah, tapi memang itu nggak bisa dibuka gitu karena memang ada aturannya. Kita nggak bisa maksa ya. Ya akhirnya kita itu jalan tengahnya itu kita mencari sendiri data lapangan untuk jadi akurasi kita gitu. Itu jalan tengah kami. Gitu. Jadi sebenarnya intinya satu, akurasi itu aja.
Itu sih sebenarnya bukan intinya. Kerjaan berat itu Bu.
Permintaan mereka akurasi harus di atas 90.
Wah.
Harus 190 Pak. Ya memang iya sih kalau misalnya, tapi sebenarnya mereka juga bilang asal tahu errornya berapa, kan bisa ada konversi ya, konversi berapa errornya sehingga kita bisa menghitung gitu loh. Itu aja sebenarnya.
Mungkin satu lagi ada uncertainty map ya Bu ya, ada uncertainty analysis. Jadi setiap pixel juga ada berapa sih ketidakpastiannya begitu.
Iya, terus satu lagi kita kan sebenarnya kita sekarang menggunakan untuk productivity ya, kita hanya menggunakan single parameter. Hanya backscatter saja kan, dan saya tambahin dengan ekosistem gitu kan, apa seperti padi irigasi, padi rainfed sama padi rawa gitu kan. Nah sebenarnya ini banyak sekali ada varietas padi itu juga harus diperhitungkan karena masing-masing varietas padi kan dia juga punya apa namanya produktivitas yang berbeda-beda gitu, masuk juga aplikasi pupuk dan lain-lain itu juga harus masuk gitu loh. Itu yang
terima kasih Bu Sasa. Saya mohon maaf nih kalau lanjut terus ini bisa sampai lewat maghrib Bu Sasa ya. Jadi kami berikan kesempatan kesempatan kepada Dr. Manzul mungkin untuk melakukan wrap up dari sesi hari ini karena waktu sebenarnya sudah lebih dari 5.30 ya. Maybe Dr. Manzul, please we will give you if it's okay for you to give a wrap up comment for the whole day session. Dr. Manzul. Okay. Looks like he's busy. Mungkin sekali lagi kami ucapkan terima kasih ya kepada Bapak Ibu yang sudah dengan setia mengikuti kegiatan knowledge sharing dan capacity building mulai dari pukul 1 sampai hampir pukul 6, dan seperti biasa setiap hari kita selalu lewat waktu ya. Kalau saya pribadi senangnya datang telat tapi pulang tepat waktu, biasanya begitu. Tapi ini karena sangat menarik ya, pulangnya telat tidak apa-apa ya. Walaupun saat ini di rumah ya sudah pulang dari tadi. Sekali lagi kami ucapkan terima kasih kepada para narasumber, pada peserta juga sudah berpartisipasi. Mudah-mudahan apa yang kita diskusikan hari ini bermanfaat ya bagi kita semua. Kami tutup dengan ucapan alhamdulillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat malam ya. Terima kasih. Saya serahkan kembali kepada Bu Nancy.
Ya, terima kasih Pak Hadi. Sepertinya jam-jam seperti ini yang sangat kita sayangkan ya, sedang hangat-hangatnya diskusi, tapi harus kita selesaikan juga. Mungkin ajang ini juga jadi satu perkenalan begitu bagi teman-teman di Indonesia dengan teman-teman di Italia. Kita sudah saling berdiskusi bersama, saling mengenal satu sama lain, dan mungkin ke depannya ada kesempatan lagi untuk bertemu, kemudian membahas yang lebih intensif lagi. Terima kasih kepada Ibu Sasa, Pak Dede, Antonio, thank you very much. Dan Bapak Ibu sekalian, sayang sekali acara ini harus berakhir di sini. Demikianlah acara pada hari ini. Besok kita masih akan melanjutkan untuk satu tema kembali, yaitu menarik dan aquaculture yang tentunya tidak kalah menarik, mengenai pemanfaatan pengiraan jauh dalam mendukung sektor kelautan. Untuk acara besok masih menggunakan link Zoom yang sama dan masih disiarkan secara langsung melalui YouTube PUSFATJA LAPAN. Demikian, saya selaku MC mewakili seluruh panitia, kami mohon maaf apabila ada kesalahan. Saya pamit undur diri, sampai bertemu besok kembali. Wassalamualaikum warahmatullahi wabarakatuh. Selamat sore, tetap jaga kesehatan dan patuhi protokol kesehatan. Salam sehat dan terima kasih.
Terima kasih. Mohon izin pamit.
Thank you very much.
Thank you.
Thank you.